Everyone doing tonight? Feeling good? Feeling confident?
No.
Okay, well you will hopefully soon, right? Just before we get started, I'm ditching this mic again. Before we get started, just to recap on what we're going to go over today, this may or may not be in order because we just changed it, but we're doing recurrences, summations and algo analysis, binary trees and binary search trees, AVLs, and I'm missing one more thing. Sorting. So those are our topics for today. We have the room 3 to 7 today. Note that that's longer than yesterday. We do not want to keep y'all here till 7. We're going to try to get you out of here by like 6. But if time runs over, if y'all have questions, it is what it is, right? Another announcement I have to make, unfortunately, the recording from Tuesday night got corrupted. So if you guys are looking for that recording, it's not going to be up. But I see a lot of familiar faces, so hopefully y'all were here for that. If you need information on DMA up to recurrence, we did the exact same sort of format for our summer exam workshop. So we'll go ahead and re-upload that in place of this. All right?
Okay.
Everyone seated? All good?
All right. I'm going to keep using the mic since I feel if I keep yelling, I'm going to get sick tomorrow. So.
Give it a minute. You got to wait for these guys to go quiet.
Yeah. All right. Is everyone seated and ready? All right. So day 2, let's begin. So starting off, we're going to go over algo analysis. So essentially, algo analysis is when they will give you a question, they'll either ask you about a specific, they'll give you a runtime of a program, and then they'll ask you, given different inputs, take that runtime and figure out how long it would take using these different inputs. That's one of the most common questions you'll see on the FE. I think it's like always on there at least once. Don't quote me on that though. And then another generalization of this is just understanding big O notation. So let's get right into it. So big O. If I could get a show of hands, I'm sure you all know big O, but let's say you're iffy with it, right? Or let's say you're good with it. Like you're confident in big O, raise your hand, right? All right, so around half people. So it's not that bad. If I had to explain it really, you're kind of just looking for key factors within code to see what is taking up the majority of runtime. So usually you would just look everywhere there's a for loop or recursion. Those are the main 2 things you're looking for, since that usually takes up runtime. So let's look at this slide right here, and let's understand big O from the start again. So essentially, let's say we had a runtime in our code that was something like 4n squared plus 3n minus 5. And each of these numbers kind of represent an iteration. So like minus 5, you could imagine like 3n minus 5 would be a loop, and minus 5 is like you have to do 5 less iterations than whatever n is. So n is like if you have some input and you're looping through that input. So just a for loop that loops through 1 through n, that would be O of n. So if you had like 4 for loops that loop 1 through n, that would be 4n. But O of n, or big O notation, will get rid of constant factors. So that 4 gets dropped, and you'll just be looking at O of n. So essentially, if you look over here, the 4 from n squared gets dropped. 3n is insignificant compared to n squared, and obviously 5 is insignificant to n squared, as 3n is insignificant as well. So this gets simplified to O of n squared as more or less your worst case. Or, yeah, this gets simplified to O of n squared. Now there's a O of omega, O of theta, and big O, but I believe, I don't think I've seen questions where they really ask about omega or average, especially not average. Sometimes they might ask you for best, but average, more or less, don't worry about it. Just hope you don't encounter it, right?
The only thing you need to know average for is quicksort, but I'll go into that.
Yeah, so that's more when you look at sorting and specific algorithms that you'll need to know the average time complexity for, but they won't really ask you a question where you have to figure out the average time complexity of some code that they give you. Okay, well that's just a quick overview. Let's move on to trying to evaluate something. So as I said previously, if you go and look at the loops here, that really tells a lot about a program and its runtime. We're not worrying about space complexity. The FE does not test on that. Space complexity, if any of you are wondering, are just how much space your program takes. So I'm not going to be talking about that, just time complexity. So what it says right here is look at for loops, evaluate any loops that run to some variable, not a constant, and look for operations like outside of the loop or inside the loop, because those may be important. So for example, maybe you have two loops and then you may say, oh, I looked at the loops, I don't need to look any further, but maybe there's like a recursive call in here, and then your entire time complexity gets a lot more difficult. And we'll get into that a little later, which we go into recurrence, which is recursion time complexity. Okay, so let's take a look at this example function. Let's figure out what its big O is. Anyone have any ideas? N squared. So why would it be n squared? Yeah, so every single time you loop, so you loop from here, from 1 to n, and from looping 1 to n, you'll have, when you loop from 1 to n, that's O of n, right? So you could say in here, your O of n, your time complexity is O of n if you ignore this for loop. But then for O of n, each time you loop, you'll have to loop n again. So for example, for every n, you could imagine that there is another n that you have. Excuse me, guys, do you have a question? You guys have a question?
No, we just argue all the time.
We're just talking about the function.
Yeah, if you could be a little more on the quiet side, that'd be good. Thanks. So, yeah, essentially, this will loop n times, and yeah.
I just have a question. For the second for loop, like let's say we put j equals to I, would it still be O of n squared runtime?
Yes. So that's a little bit more complicated case, but essentially it would boil down to being the first iteration would be n, then the next would be n minus 1, n minus 2, n minus 3, n minus 4, and so on. And I think you could write that as a summation, and then if you kind of put it, pull it down into its factorized form, then it turns out to be n squared. So for something like that, if you see j is equal to I, you have to get a little bit more complicated and start using summations and stuff. But that's our next section, using summations. All right. Any question? Oh yeah, I guess you guys would have questions. You would raise your hand if you did. So let's move on. So evaluating algorithms. I talked about this at the beginning, saying that they'll give you some runtime, and then they'll tell you, given some inputs, how long will a certain program take. So realistically, it all comes down to algebra. It's algebra, college algebra again. So once you figure out the runtime and your inputs, you have to solve for some imaginary variable c. Just say that's how fast your computer is. That's how I like to think about it. So how fast is somebody's computer? If you run a program on some input, it'll have like some constant it multiplies by, and it'll show you how fast the program should run with different inputs. And I'll show you an example of this when we're doing a problem. So you'll understand a bit more of that when we get to it. Okay. Is this the same slide? It is the same slide. Okay. This is also the same slide. All right. All right. Problems. Let's get right into it. So first we got evaluation 1. So this is the first type of problem where we'd have to evaluate the runtime. So let's let me switch over to the iPad here and start evaluating. I had a couple complaints last time that it wasn't the best visibility, so is it looking good? Okay, cool. So let's read this. So what is the best and worst case? It's not for full text. Being not so smart. Just trying to zoom it out on the screen share. So what is the best and worst case runtime for the following algorithm? In terms of the input parameter n, you may assume that an array, that the array pointed to by array is of length n. Give a brief explanation for your answers. So let's look at this. So they give us a function called foo, which is typically just used as something like an example. It has a return type int, and we're getting passed in 3 parameters. So an array, and they told us it's of size array. They told us it's of size n, and they're also passing in a value. The value doesn't seem to have any significance at this moment. All right, so next line of code we have here. So we have current equals to 0. I don't know what that does yet, but we'll find out as we go. Then we have jump, which is equal to n divided by 2. So we know that n is kind of our input and what we're going to be basing this around, since it's the length of the array and they give it to us, and it seems that this loop, I looked a little ahead, is also based on this jump, which is based on n. But let me slow down a little bit. I think I went a little too quickly with that. So essentially we know that we start our jump at n over 2, and while our jump is greater than 0, then we'll keep running this function. So our runtime has something to do with jump. We know this. So let's look at this if statement. If value is greater than array at current, cur plus equals jump. So this doesn't matter. We don't care. Why do we not care? Because we only care about what happens to jump. We're changing cur, and cur doesn't seem to do anything for us at the moment. Else if value is equal to array at cur, return cur. So now actually we care about this just a little bit, but not fully. So the reason we do is because if we return current here inside this while loop, that means we will automatically exit the function. And normally if we were looking for worst case, that's not important, but they did ask for best and worst case here. So let's analyze this a little bit more. So they told us that array at cur is going to be, or array is of size n, and that's all we know. And presumably it has some values inside of it. Uh-oh, what did I do? I cleared it. Oops. All right, hopefully you guys remembered what was drawn. I'll try to yeah, so while jump is greater than 0, that's what we care about. If the value is greater than array at cur. So what does that mean? So they give us some value in the input, and if it's greater than array, or the index in the array of current, if the value inside the array at current is less than that value, then we'll add something to current, so our jump. And otherwise, if that value is equal to array at current, or wherever our current index is, we'll return. So we could kind of assume what happens, what's the best case here? Anyone have any idea? What's like best case, it runs shortest time? Yeah.
O of 1.
Yeah, so what would be the case where it runs an O of 1?
Where we just find it immediately, like that's the first value we check is the value that we want.
Yeah, so if we jump into this loop and immediately we find that our value is directly equal to whatever the current in the array is, then we will immediately return that current, and then the function will just dissipate. But let's say, so that's our best case. So our best case would be O of 1, and because of this return statement, we could write some explanation here. Because they didn't tell us, they just told us to write like a best case explanation. All right, so we got our best case. But now, what about our worst case? So our worst case would be under the assumption that we never find this else if statement. We never return. So we have to exit out of this loop. So at the end here, we see that jump gets divided by 2 every single time. So jump starts at n divided by 2, and then in every loop, every iteration, it gets divided by 2 again. Going to n divided by 4, then divided by 2 again, n divided by 8, and so on. So if you looked at these questions for a little while, you would kind of understand that this is logarithmic behavior, but I'll go into exactly how you could see that it's logarithmic behavior. Yeah? Yeah.
It's kind of the opposite of like exponential in a way.
Yeah.
The exponential just kind of doubles or something every time.
There's a certain answer that yeah. So you could kind of just say that, and in your explanation, and that should work. But there is a way that you could actually do it via just having a variable as iterations and figuring it out directly using like an equation. So a little bit more than just intuition, something to give somebody who maybe doesn't have that intuition yet a chance to get through it. So we could kind of imagine that we have a variable called k, and that's our iteration. So at iteration 0, n is this. At iteration 1, n is this. Iteration 2, and is this, and so on. So we could kind of model this as a function where we have n divided by a function in terms of k. So n divided by 2 to the k plus 1. Let's n divided by 2 divided by 2 to the k. Because we start at n divided by 2, and each iteration we will divide further by 2. So since k is the number of iterations, we go this way. And then when do we want to end this? So we want to end this when jump is greater than 0. So essentially when our iteration when we hit 0 is when we want to figure out our worst runtime. It's when jump goes all the way down. So as you said, with intuition you could figure out it's logarithmic, but mathematically you could set this equal to 1, and you would set it equal to 1, not 0, because if you set it equal to 0, then really everything you do here is just going to be swallowed up by that 0. But 1 is like a good approximation. So sure, it says jump is greater than 0, but if this is equal to 1, then immediately after, the next iteration is going to be the iteration that gets out of this while loop, sort of what I mean. So you can imagine this equation is 2 to the k is the number of iterations, and after some iterations, you'll have your worst case, or you'll get out of this loop. So all you have to do is solve for k, and then you get the number of iterations. And if you don't really want to do this and you can intuitively tell it's logarithmic because it's constantly dividing by 2, you could just write you could say it's logarithmic because it's going down by 2, and you don't have to do it mathematically. But this is a way you would do it. So then you'd move 2 to the k to the other side. You have n divided by 2 is equal to 2 to the k. Sorry, my handwriting is getting more and more skewed. Let me straighten it back out. So we have n over 2 equals 2 to the k. We could multiply 2 to the other side, get n is equal to 2 to the k plus 1. And then we can apply a logarithm. So log of n is equal to, we could say base 2, right? So that's how you would cancel out this exponent. And then that would equal k plus 1, because we would have the logarithm on the other side, base 2, and that would kind of cancel out the 2 and leave the top expression here. And then all we have to do is now subtract the 1 to the other side, and we get our runtime. And our runtime would be in big O, so we get rid of the constant, so it's just O of log n. And you could put the base 2 there if you want. But yeah, that's how you'd solve the problem. So our worst case would be O of log n, and our best case would be O of 1. Anyone? Yeah, sorry, I wasn't looking that way.
No, you're good. For the explanation part, how detailed should our explanation be? Should it just be one sentence, or should how thorough should it be?
You could make it one sentence. The TAs should award credit. I wish we had a TA in here that graded the foundation exam before. That would have been nice. But they should award credit. They should be lenient, as they want to give you points. They'll try to give you points if they can. If they could understand that you had the idea, you know what you're doing. If you write one sentence or 2 sentences explaining your idea, then you should be good. Okay. Yeah.
2 questions. Would our word for getting to log n, would that be enough for the explanation, or you actually have to write a sentence?
Yeah, you have to actually write a sentence. Yeah, you'll see in the solution slide next what they wrote. It's kind of a lot, but you don't have to write that much. You could write a sentence, and once again, if you have the intuition for it, and you could sort of explain why, just so the person reading it could understand, then you'd be good.
Leo, question.
Yeah.
So a lot of times when we're doing these questions, it'll say like either give an explanation or justification, and sometimes they want a mathematical explanation, sometimes they want a word explanation. So how would I know something different?
Will they, you mean like, have you seen questions where they explicitly told you the mathematical?
No, they'll just be like provide like justification or like an explanation, and then like I see sometimes it's word, sometimes it's math.
In the solution, sometimes they'll put math, but that doesn't necessarily mean that you need to put the math to get the credit.
Okay.
Yeah. So as long as you could explain it enough, then you should be good. Otherwise, they will explicitly like tell you to put math, or usually it would kind of be impossible to kind of get that from words. Kind of like if you added like one caveat here somehow, I don't know what I would change to this function, but there could be a way that makes it kind of impossible to get the exact runtime from intuition, and you actually have to do the math. But if you really don't know how to do the math, then you wouldn't really know how to solve the problem in the first place, so you could just write it with words. Always write something, get that partial, all right? That answer the question? Okay, cool. So let me switch.
Another one.
Another one? Yeah.
For best case, could it also be O of 1 if n was equal to 1, so it would just like jump was not greater than 0?
Yes, but then it's like n is a variable, or it's, I didn't mean it in the sense of like, that's a variable, obviously you know n is a variable, but I mean it varies. That's what I meant by that. So it's a parameter that gets put in, so you can't really say anything about just saying, like if they told you n could only be 1, sure, it's always O of 1, but n could be anything. But yeah, you're right. If n was 1, then it's O of 1. But it's also log of n, because if you think about it, log of 1 is, well, it's 0, but it's something like that. That answer your question? Yeah.
That'd be specifically because it's in terms of n for the O runtime, right? So if it was like in terms of a different variable, then you could say, because I've seen questions where it's like, best case is if I is equal to j, and that's not what the runtime's measured at.
Wait, could you repeat that question again? Sorry.
Is the reason you can't like set, like say the best case is n is equal to 1 because it's measured in the big O runtime, but that it says in terms of input parameter n?
Yeah, so because it's a parameter, and like let's say they gave you that this was a constant, or let's say they in here wrote int n is equal to 1, and then this wasn't here, then yeah, it would always be O of 1 because the jump would equal 1/2, and then integer division would make it 0, and then jump would never be greater than 0, so then it would always be O of 1. But n is not guaranteed to be 1. So yeah, what you're saying is right. Does that kind of make sense? Or are you still confused? Are you?
Oh yeah, sorry.
Okay. Okay. Any others? Okay, cool. Let me move back to the solution. So over here you could see the explanation that they gave for that question. So over here it says the best case runtime is O of 1, as we found out, and the worst case runtime is O of log n. And let's see what they wrote for their explanations. It's possible that the very first loop iteration, that the else if clause that returns cut, cur, triggers, and in that situation it would run or end the function immediately. And the worst case, they do the math, but each time, the number of times the loop runs is controlled by jump. Each time jump value is divided by 2, and the loop will end the iteration after jump equals 1. So you could kind of like ignore everything after that and kind of just say your intuition. And over here in the grading, it says 1 point for best case answer, 1 point for its justification, and 1 point for worst case answer 2 points for its justification. So they give you partial, even if you have a bad explanation, but you would have the answer. And right here they say justification. So anything, it doesn't have to be math. All right, let's move on. So another one. I'm not keeping track of the time. Oh, I have it on my screen on this computer right here. Okay, cool. I gotta kind of speed through this because I gotta catch a class after it hits 4:30. I'm not gonna lie. Then Dylan's gonna take over. Okay. So what is this problem? Let's move back. A program takes O of n log m time to process n data sets. Each n data sets, each with m values. So they gave us the runtime n log m and the time to process n data sets, each that have m values. Then they tell us for 100,000 data sets with each with 2 to the 16 values, the program takes 500 milliseconds to complete. So let's just digest that real quick. So 100,000, okay, real funny. Okay, 100,000 data sets, that's our n. And then our m is 2 to the 16. And it takes us 500 milliseconds to complete. Now, we have our n and our m, so we could just plug it into the O over the runtime that they give us. So we know that 10 to the 5, which is 100,000. You'd want to write in scientific notation usually on these. It helps a lot. And log of 2 to the 16. Now, sometimes you could assume, I'd say don't assume that log is base 2. In this case, it's actually base 10. They say that in the solution. But at the end of the day, your answer will still be more or less like the same thing if you assume it's log 2, log base 10. But I'll just go through it with log base 10 as it's intended. But if they don't explicitly say it's log base 2, then you might want to assume it's log base 10. And if for some reason you're getting stuck, you can make it log base 2 and kind of continue through the problem if you want to get more partial. Okay, so what do we have here? We have the runtime that they gave us, 10 to the 5 times log 2 to the 16 is supposed to equal to 500 milliseconds. But if we look at this, 10 to the 5 log 2 to the 16, if we multiply this, if we do the math, I don't know exactly what it is, but it's not going to equal 500. So something's wrong here. We have to find some constant that gets multiplied by this that makes it 500. And that constant is the time it would take on that computer to process everything. And you could think of it as like each computer has some constant, and that constant would be multiplied by the runtime to give you some time. And that constant is what you're finding. You could kind of, did I just do it again? No way. This sucks. Okay, I could write that back real quick. So 10 to the 5 log 2 to the 16 is equal to 500. And then times a constant, and this is milliseconds. Oh my god. Handwriting be damned. Okay, so you could think about it whenever you encounter a problem like this. You could just put n and m into the runtime and equal it to the time. And if you see it's not equal to the time, then it needs some constant. You need to multiply this by something to get it to 500. And that's how you could think about these problems. And then after that, you just solve for C, and then we'll continue for the second thing that they asked us. So they asked us, given this information, how many milliseconds would you expect the program to take to process 60,000 data sets, each with 2 to the 20 values? So they give us a new n and m, and they want us to find how much time. And that time is dependent on how fast the computer runs, you could say, or this constant C. So we'd want to solve for this constant C next. So any questions thus far? because then everything after this is basically just going back to algebra, which I hope I get right. So let's solve for c. Essentially, you could divide by 10 to the 5 and log 2 to the 16. Actually, wait, hold on. This could be log 2, and then we could pull out the 16. Sorry if it makes it a little clunky. And then we could divide the 10 to the 5 by 500 milliseconds here. And then, what did I, my bad. Okay, then we could divide the 16 here too. And then we could divide the log as well. Now, about simplification here, you can simplify by like the 500 is 5 times 10 to the, that is not a 5. 5 times 10 to the 2. And you could kind of simplify from there. But in this particular problem, I remember looking over the solution. The simplification is kind of like, if you simplify it, it's going to make it harder later on. I remember simplifying it, and then I screwed something up, and then the problem was wrong in the end. And I'm like, what? What did I do wrong? No way. But usually if you could see something that easily simplifies, then you should. And honestly, I'm going to take my own advice. I'm not going to take my own advice, and I'm going to simplify this 10 to the 2 because I'm lazy. So let's see if I get screwed over or I don't. But usually you would want to simplify because it makes life easier. So the 10 to the 2 over 10 to the 5, that would simplify this 5 to a 3. Okay. So now we have, in case you can't read this, because once again my handwriting is terrible, 10 to the 3 times 16 times log of 2. That's log base 10, by the way. Usually they would tell you if it's log base 2. Okay, what do we do next? That's our C. So this is the C we solved for. Next, we have to go and find how long it would take for 60,000 data sets, each with 2 to the 20 values to run. So now that we have our constant, now we could just go ahead and write this out as our n is 60,000, so 6 times 10 to the 4, and then times log of 2 to the 20 times our c. It's supposed to equal to something we have to figure out. Now, here we are given we could plug in the value of c that we have here, and then we get 5 over 10 to the 3 times 16 times log 2. This is going to get hard to write on. I should just zoom in more. Okay. So 6 times 10 to the 4 log 2. Let's get rid of this. This 20 can go down based on log rules. So times 20. And then times 5, the 5 from the c. And then that all is divided by the things that are divided by the c. So the divisor here. That's 10 to the 3. Oh my god. I wish this could be thinner. But that's technical issues that we haven't figured out for this year, I guess. 10 to the 3 times 16 times log 2. So now you can see the logs cancel out here. So even if it was base 2, base 10, it doesn't matter. They got canceled out in the end anyway. Then this is 10 to the 3. I think what they ended up doing in the solution is they actually merged this 10 to the 3 times the 16, and then they were able to simplify it much easier. But personally, I don't know about you guys, but I don't see how that's obvious that you would multiply the 16 by the 10 to the 3 and then you'd get that divisor. But it's okay, because as long as you have some formation of an answer, then they should still give you the credit. So because Let's cancel out the 10 to the 3, and this would become, this is a 10 to the 4, it would just become 10. So me crossing it out. So we have 6 times 10, 60, 6 times 10, times 20, times 5 over 16. Okay, that's not that bad. 16 is just 4 times 4, right? So then 4 over 20 would be, that would simplify that to 5. And then we have 60 times 5 times 5 over 4. Yeah, and the 4 would also simplify with the 60. So that would turn into 15. So then we have 15 times 5 times 5. 25 times 15. 250 plus 125. Yeah, 375. Thanks to the people that pointed it out. So 375 milliseconds is how long it would take. So really, after you figure it, it's just algebra. These problems are just algebra. And they give you 10 points for that. That's a 10th of your exam, right? Pretty hype. You just got to remember algebra. Hopefully you guys get a question like this, in case you like that sort of question. Any questions about this? Okay, cool. So let's move over to the solution. So 375 milliseconds, I did not screw it up. But just so you could look at the partial here, just for setting up the equation for the constant, they give you 2 points. If you solve for C without simplification, they give you another 2 points. If you plug in the values, they give you the 2 points. And then on top of that, at the very end, I don't think you even have to simplify fully for the 4 points. I think if you leave it in some unsimplified form, they could give you some of that. Yeah.
So let's say you make a mistake in C, but you plug it in correctly with the wrong value.
Yeah, they'll give you credit.
Alright.
Yeah, so if you screw up C, but you still plug it in, that's why the partial's there.
And if you answer everything with the C, but C being wrong.
They'll give you partial according to this. So the professionals will write this grading scale, and you kind of get, so you get the 2 points for setting up the equation for the constant. You get 2 points for solving for C. They didn't say it had to be correct. Plugging in the appropriate values to solve the problems, you get 6 points, even if you get it wrong, as long as you did everything right. I think. I wish a TA would be able to correct me. Yeah. Okay. Any questions? That was algo analysis. Yeah.
Can you go back? I'm curious about the way. Why did they do that?
Yeah, I don't know. I honestly don't know. I don't know why they turned this into 3200. They had some gap in logic that I couldn't see, and honestly, I don't know if any of you saw it either. But yeah, the 3200 here, why they multiplied the 10 to the 3, that was simplified. If you remember, we had a 10 to the 3 and times 16. Oh wait, I actually don't know what they did here, but it arrived at the same answer. As long as you have your algebra rules with basic, you'd be good. Okay, I'm running a little low on time. I gotta catch my class in 30 minutes, so let's keep going. No more questions? Cool. Oh, did you? Okay, summations. This is a short one. There's only one question here, so I'm just going to breeze through this. It's called section 6.5 because it helps with recurrences. Yeah. So summations, I believe they'll give you the formula sheet on here. So essentially you just memorize. You don't even have to memorize. They'll give you the formula sheet. It will be at the front of your FE, and I don't remember exactly where it is, but Dylan, could you correct me? It's at the front of your FE, right? Or it's a separate piece of paper. I'm not sure. Yeah, it's at the bottom. Yeah.
So I just have a quick question. So the formula that we get for when there's something to the I is to infinity, and I know that's popped up a bunch of times, but usually our summation is to the n. Am I just allowed to like make it to infinity and use that formula?
I think
There is a formula to the n, but it's not on here.
I think I actually did that on my exam.
Okay.
But hold on. Yeah, because if you're going, Sorry, I'm interrupting a bunch of people. Here, let me answer a question first, then I'll answer yours. So if you're going to the n, if your n's like really large, then you could technically say maybe your n's approaching infinity, because as you're going through this geometric series, it's like it goes lower and lower and lower every time. So you can technically say that. I remember I did that on my exam, and I know I got credit for it. So essentially, you can use it. But if you know your n is really small, yeah, I'm not sure. Maybe you remember some of your calc too. But yeah, you could use it. You'll get the credit. Yeah, we'll see some. There was a nasty recurrence we saw when looking over recurrence questions, which is the next thing, and it required you to like remember some calc 2 logic from way back, and it was just horrible. That was from an exam from like 2020, I think. So pray the professors aren't evil to you today, or this Saturday. Okay, let's explain what these are. So if you guys don't know what summations are, in case none of you know, it's essentially just you go from one value to another. It's a loop. It's a loop. Summations are loops. You go from one net value to the other, but every time in that loop you add that value based on like the value here. So I'm gonna look at the summation split here. So k is equal to like, let's say 1. Let's say a is 1 and b, let's say the b ends at 5. So each time it would be like f of 1 plus f of 2. What am I saying? F of 1 plus f of 1. Then the next section, it would be f of 2 plus f of 2, and so on. Everything would get summed. And at the end, you'd get the sum. And these are important because when you're doing recurrence relations, you're kind of going in like an iterative step. And sometimes you'll get into something where you could see that things are being summed based on some value. So that's important. The summation split, if you have a plus in the middle of two values like this, or a subtraction, does not work with multiplication and division. I remember on one of my CS1 professor, I had a summation, and I tried to split a multiplication. I knew it was wrong, but I tried to give some proof for it, and I still got like 20 out of 25 points somehow. So even if you can bullshit, you don't know what to do, then do it, because they'll give you partial. So a plus and a minus can be split into two separate summations. And this one is a bit complicated to explain. Hopefully some of you can kind of intuition your way to it. But essentially, a to b would be values like that. They would go from a to b for f of k. And it's equivalent from going from like 1 to b minus a plus 1, or from 0 to b minus a. And you could change your values inside of this. And the reason why is because in this original function, essentially, where is k? I think this is supposed to be a k, not an I. Maybe I'm tripping. Yeah, that's definitely supposed to be a k. Unless someone can tell me otherwise. Okay, yeah. So, yeah, this is just an index shift. When you start here, this is f of a, and then it goes to b. So here, when k is like 0, you'd start at f of a and you'd go to b minus a. So that's kind of how it works. I don't think you'll actually have to use this too much on the exam. It's just like simplification if you want to like turn your summation into something that's more readable. But hopefully you don't have to use something like this. This you might. I think one of the questions, yeah. And this is easy. You just split it. You turn it into two summations. Yeah.
I've heard of a rule before for like index shift where it's minus until you have a value when a working at the bottom.
I honestly have no idea. I'm refreshing on this myself because I had to look it over. But index shift, it's kind of like hard to explain. Like, hopefully some of you can understand kind of the intuition for it. Like, I'm trying to get across. But if you know some rules, you could search it up, and you'll get some rules for helping simplify summations. Let me keep going. So some summation series that you should be aware of. The arithmetic series, very important. Here's your question. If you have n, you could use maybe. Yeah, I think you could use the geometric series that's finite. For the person that was asking about if they have n instead of an infinite, you could use this geometric series, I'm pretty sure. Yeah, I'm pretty sure. But if you want to be safe and you really don't know and you're confused during the exam, just use the infinite one if you have a summation. But then again, these only show up on section C, so don't worry about it that much. And probably only one question at that. The arithmetic series is the most important. These are just formulas. I'm not going to go over the intuition for understanding them. So if you see like a bunch of values being multiplied by each other, or I think values that are adding by each other but going in like a series, like 1 plus 2 plus 3, those keep going up by 1, or 2 plus 4 plus 6, they keep going up by 2, that's an arithmetic series. Geometric series is like if they go up by some multiplication constant, so let's say multiples of 2, so 2, 4, 8, and so on, 16, 32, 64, and so on. And geometric series infinite is just if it goes on infinitely. So this, but without the extra 1 minus r to the n. Okay, let me keep rushing. All right, we were at the problems already. I think there's just one problem here. No, I lied. There are 2 problems. Let me speed through them. Oh my god. Okay. I'm only doing one problem here. It's gonna be too long to do the second one. Let me see which one's better to do. Which one would you guys prefer? This one? All right, raise your hands. This one? The other one? All right, we're doing the first one. Okay. Thanks. Okay. So, determine a closed form solution to the following summation in terms of n. Please leave your answer in factored form. Specifically, your answer should be in the form n plus a, n plus b, n plus c over d, where a, b, c, and d are all integers. So, this image is really blurry, but let me draw it out again. Summation I is equal to 1, n, summation j is equal to 1, j, and this goes to I. So, what's up? Oh, that's not, oh, it's not. I just didn't switch the screen. That's my bad. Okay. So, handwriting's horrible. So once again, let me not rewrite it. I'm sure you guys can read it. So, from j to I, j goes from 1 to 2 to 3 to I. That was a arithmetic series. Let me write down the formula for that. That goes I plus 1 over 2. The formula, it's the variable it goes up to, or yeah, how many of those you have. Essentially, this formula comes from just adding the first number to the n number and going so forth. So I over 2 is like half of I, right? And then I plus 1 would be the ending value in your sequence and the starting value in your sequence. So the starting one is 1 and the ending one is I. Don't want to remember that. You'll have the formulas. So I'll probably scroll back to them for. Okay. Yeah. So it goes from j goes from 1 to 2.
Can't see it.
All right, that's good. Yeah. To 3 to I. That's what the summation is doing. So use the arithmetic series since it's going up by ones all the way to I. And you do I plus 1 over 2. That's using the arithmetic series, which is this one. The ending value and the starting value, the amount of values over 2. So you have I values in here over 2, and then the ending value is I, the starting one is I. Okay. So now that's the summation done. So now we have the summation where I is equal to 1 and to n. Now honestly, I don't remember the formula for this, but it's on the formula sheet. So let's scroll all the way back here, and they told us that I squared, this one, this is the important one, because we know, we'll simplify the expression that we had there into having I squared. But I squared is going to be n plus 1, 2n plus 1 over 6. I'll try to remember that. Hopefully I don't have to scroll back here. Hopefully one of you will remind me anyway. Okay. n plus 1, 2n plus 1 over 6 is I squared. Yeah, from I equals 0 or 1? Oh my god, I should have paid attention. 1. Okay, we're chilling. No need to index shift or anything to n. So what we do now, sure, we don't have this exact form, but we could just distribute. We get I squared plus I over 2. We could factor out the 1 over 2 at the end here. We could do that since it's a constant. We don't care. And then what we have here is now I squared plus I. Any questions how we got there? Okay, cool. Now use the summation split. So now it's split into two summations. This is getting quite messy. Where we have I is equal to 1 to n of I. So this is the arithmetic series, and then this is whatever this is. So, and don't forget the constant of the 1/2 that you have to add back at the end. So arithmetic series, it would just be 1 plus 2 plus 3 dot 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 to n for I, because it would be going in that sort of iteration. So then we could write the arithmetic series as n plus 1, starting value is 1, ending as n, over 2. So that's this. That's that summation done. Now we have to do this one. It's okay, we have the formula for it. So from 1 to n, I squared, it's exactly this. This is our answer. So,
we have a question.
yeah.
Are you, whenever you split the summation, are you timing the 1/2 on both of them, or just one of them and expecting that to show?
So there's supposed to be parentheses around here. Hopefully this will answer. So it's supposed to look like this. Yeah, so it just distributes. Because you could imagine it as you took out the 1/2 before you split it, and then you split it. 2n plus 1 over 6. And there's a way to simplify this. Just multiply this by 3 over 3. You get 3n, 2n. Wait, what? 3 it's not 2n. You're right. 3n plus 1 over 6. And then you just add it into there. So now we have like n plus 1, 2n plus 1, plus 3n, n plus 1, all over 6. And there is simplifications here. I know it. Do I know it? No, maybe not. Was it supposed to be... Hold on. Yeah, I think what I do is just I have to go distribute to get to the actual answer. Because my answer right now does not look. I don't think it's the solution. It might be if it's simplified. I'm not sure if I remember. I really hope it is. I just erased something that shouldn't have been erased. Okay, I'm gonna get to this quick so I could at least start on recurrence, and then Dylan could finish that off for me and continue.
I'll take this slide.
Okay, he's got it. Okay, so I could be a bit lax here. So distribute that n there. Then we have n squared plus n times 2n plus 1 plus 3n n plus 1. So let's distribute this That's going to be 3n squared plus 3n. Oh my god. Okay. 2n cubed plus n squared plus 2n squared plus n over 6. Okay, just for time's sake, if you get a question like this and you get to an answer and you have other questions that you have to do, don't simplify it, just keep moving. It's going to take time, and then you could go back to it, right? Because you're wasting precious time. You could be working on other questions, doing something that you already know how to do, right? What if you encounter something that you actually have to think on?
If we were to write that out, would we get partial like points for that?
Probably.
Yeah.
Surely. Yeah, Oh, I forgot to multiply this 1/2. That's why it was looking weird. See, I almost forgot that. Okay, this is supposed to be a 12 after you did that. Then let's continue simplifying since I got time, since Dylan's taking over recurrence. That's 5n squared, 5n cubed. That's both of those. We got 3n squared plus 4n. And then you factor that and all over 12. And then you factor it. I'm not going to do that. You guys know how to factor, right? If you guys want me to factor it, raise your hand, because Dylan's taking over recurrence, I got time. Factor?
Yeah.
All right, chat. All right, I do my factoring a little weird. So, I remember I take, oh wait, you could factor out an n from here. So you have n, 5n squared plus 3n plus 4. Then this is all over 12. Then if you factor this, I think what I did is I have some weird strategy where I find two numbers where I cross multiply, and then oh my god, I haven't done this in so long. Alright, alright, actually, you know what? It's alright, I'm not going to embarrass myself. I have the thing, and I'm just going to distribute it and show you that it does equal this, hopefully. So, n plus 1, n plus 2. This is not looking good for me. I definitely messed up somewhere. Okay. Hopefully you guys won't blame me. Do you see where I messed up?
No, your solution's over 6.
Oh, that's why. It takes out a 2. Hold on. This is over 6, not over 12. Maybe I'm still right. You guys want to have hope for me, or do you guys want to move on? Are you guys invested in the story? Yeah. This 5 came from adding this 2n cubed plus. Oh. That's not a cube. That's not cubed. Okay, you're right. The 5 came out of nowhere.
I think it's done.
I think I'm cooked. I'm cooked, Chad. Okay. I do not want to go back to this. All right, let's see how much partial.
Half the points.
How much partial did I get? Let's see. 1 part inner sum. Okay, I got 1 point. I did. Okay, I did this. I got that. We remember that. 1 point split sum. Okay, I split it. I did that. Yeah, that was me. Okay, that's 2 points already. 2 points. Plug it into I squared formula. All right, 4 points. 4 points. All right. We plugged it in. Then 2 points plug into I formula. Oh, another 2 points because I plugged it into here from the split one. That's 6 points. All right, and then I think I screwed up the answers, so I don't get those 4.
Yeah, so you could have partial, you might gotta.
Oh, and decide partial as necessary. I'm gonna decide 4 points partial for myself and give myself 10 points. All right. So, as you can see, realistically, you'd probably get like 8 here or 9. So, even though I got a completely wrong answer, the whole process there was more or less what they wanted. So, you screwed up your algebra. The base of all mistakes. Oh.
Just use your phone for your safety.
Yeah. All right.
Take my phone. Give me the mic. And then here you go. Good luck, man. I'll take it over.
Let us swap over real quick and I'll pick it up where we left off.
Could you go grab me my monster by Caleb? You want someone sitting up here with you? Sorry for the static. Hopefully this works for me as well as it worked for Leo, because I don't want to have to yell.
Yeah, I'm glad I didn't have to yell. That's gonna save my voice. So.
Alright, just let me get my bearings real quick.
Bring my laptop.
Alright, thank you. Alright, cool. So, I'll let you get out of here, Leo. You good? I'll let the commotion settle real quick and then we can pick up to the next thing. Who's excited for recurrence? I feel like this is the least favorite topic. It's definitely mine, which is why I'm really upset that Leo left it for me, but it's fine. Huh? Okay, thanks. Because I need a camera. Alright, so I put the little disclaimer out there, right? Leo left me with this, but I was reviewing everything last night, just in case he did. So hopefully I can pull through here. So I'm gonna move my mic over.
Borrow that sweater real quick. That's mine. I'm gonna be freezing outside if I don't take that.
All right.
Leo, what's up? I don't need it. Why would I take it to class? Take pictures of Lineker?
Okay. All right. Is my mic working okay? Are we good? I hear that weird ringing in the back. I don't like it.
Is this your monster?
Yeah, it's mine. Yeah. I'm ditching it. I really don't like the way the mic sounds. Can everyone in the back corners hear me fine? Especially that one over there. Y'all hear me good? My voice gets tired? I'll try the mic again. Maybe it'll agree with me. All right, so recurrence. I'm going to go back and do a little recap on algorithm analysis because there are a few things here that, quite frankly, throw a bone in the whole process of doing this, right? And that's recursion. So analyzing recursion using code is not something that's like looking at the code and just kind of having that intuition is not something that just naturally happens because there's all of these different branchings and all of these different things, the recursion trees. And when you're considering something like super complex recursion, you're not going to be able to understand it conceptually without a lot of heavy lifting. And so that heavy lifting is done for us in the form of recurrence relations. So this is essentially the way that we define runtime for recursive methods, right? Recursive functions. Because the way that recursion stops is a lot different than maybe something like a while loop having a break condition. Even though recursive functions do have the base case, all of the stuff in the middle can be very, very different compared to something iterative because of the way it branches. So that's kind of the reason why recurrence was sort of born as something that we need in order to analyze a function that's recursive. So the way that it's going to work essentially is this right here is you could almost imagine it as your recursive case, right? Imagine that this is a function. Your recursive case, show of hands who was here for the last session. I'm going to be using a lot of the same terminology that I do for recursion because that's just how my brain works. So hopefully y'all can follow along with that. So this is the recursive case. Imagine the input is n, as said right here. You could this is just a function. It's a recursive function. So this is your recursive case. You can imagine we're calling t of n minus 1, and then the factor of how many times we're calling it is in the front, right? And this is for n greater than 1. So that's kind of going to be our base case in our mind here. So t of 1 is saying that when n equals 1, return 1, right? This is our break point. This is where we're not doing that recursive step anymore, and this is when we can start on our way back up, starting to deduce what the actual runtime was, right? So this right here is a really important piece of a recurrence relations problem. When does the base case get hit, right? When are we stopping and when are we starting to do all of that math? We need to solve for that specific point in time when we hit there and everything that we've done before it. So I don't even know what's on these slides because Leo made them. Just making sure I hit all my points. So the way we arrive at runtime for recursive code, as I said, same as functions except, base case recursive step. Awesome, I covered it. So the way that this is going to go ahead and work is you want to perform a minimum of 3 iterations on the exam. And I will define what an iteration is, but essentially you're plugging the function into itself as its recursive step. You could almost imagine we're solving for each node in that recursive tree that we drew, right? And we're trying to find the biggest one, because really with runtime, you want to find how long it's going to take from the top node all the way down to the bottom, right? So that's kind of what we're solving for. We're going to keep calling ourselves, we're going to keep iterating, and we're going to find the value at that point. So you want to perform 3 iterations. I say 3 because by minimum, you're going to be asked 2 for partial credits. If you do 2 iterations, that's already 4 out of 10 points. That's pretty nice. I usually recommend doing 3 because I don't think a lot of the times you can see the pattern with 2. For some of them, you can. If it's like +1 each time, like, come on, you got that. But when it's something a lot more complex, I personally recommend doing 3. By minimum, you should do 2 because that's what partial is going to give you. So keep that in mind. Essentially, it's a 3-step. What's up?
Do you count as an iteration like the first one, or you do 3 besides the first one?
I don't count the first one. The exam doesn't count the first one either. So the exam wants you to plug it into itself twice. If I really don't know where things are going, I just plug it in again just to kind of understand what that end term is going to be. If you don't see the pattern, because a lot of this is pattern recognition, right? You may have a arithmetic series that you can identify or some sort of logarithmic behavior. A lot of it is patterns, and if you only have 2 samples of that pattern, it's really hard to kind of see where it's going, right? So the more, if you don't understand what the kth term is going to be, you could do 6 iterations if you really got the time, right? Just to help understand that pattern. So after you do those 3 iterations, it's kind of a 3-4 step process, right? You're going to express the iteration in terms of k, where k is the kth iteration. So for example, the first iteration is usually, I believe they say t of 1, right? T of 1 or t of 0. That first iteration, they give it to you. And the next one is going to be the first one, the one after that, the second, third, fourth, so on and so forth. You can consider that each recursive call in that tree. We want to express it in an arbitrary term k because that's going to allow us to exploit the fact that we know the base case and solve using algebra. And I'll show you what that looks like in just a sec, right? And then after you want to solve for what's inside of t equal to 1, because like I said right here, we know what t of 1 is. It's not always t of 1. Sometimes it's t of 0. I've never seen it be other than 0 or 1. If they throw you t of 4, I don't know. But that's what it is, right? So t 1 or 0. You're going to want to take whatever term is in here, express it in terms of k, and then solve that equal to 1. Once you find k, you're going to plug it into all of the occurrences in the kth iteration form. So this sounds like a bunch of mumbo jumbo, but I'm going to show you in an example, right? Okay, well, I guess he did it one by one. So three iterations right here. 1, 2, 3. Express the iteration in terms of k. So this is the kth iteration, right? And I'll show you how we get this because this is actually the example problem we use on the next slide for when I write it out. So I'll go through it. N over 2 to the k is that internal term we're talking about. We want to solve this equal to 1. So n over 2 to the k equals 1. You multiply k out. You now have 2 to the k equals n. And so now we can plug that in, right? Let me see where we find that. Right here. So 2 to the, so we know 2 to the k equals n. So now this turns into an n. N over n is just 1. And 2 to the k minus 1 becomes n minus 1, right? We want to have the entire final product in terms of n because we don't ask for O of k, we ask for O of n. So if we have any k's left in our equation, that's a factor that we don't know. We want to get that out of there, and that's how we use the base case right here to do that. I didn't put this here. Leo wants to make sure you guys always iterate 3 times, okay? You could do 2, like I said, for partial, but that was just my recommendation the year before. Why did he call them evil recurrence? Okay, well, I didn't see that. I was going over them on my phone before I came up here to hopefully be prepared, but I don't know what's so evil about these. Hopefully Leo didn't leave me with like some really sick and twisted recursion problems, but he probably did. He probably did. All right. So, y'all ready for evil recurrence 1? I fear that for evil recurrence 2, it's going to be harder than this because that's usually, you know, you increment, you go up, but we'll see. So, again, we're going to identify some important things for us here. This is going to be our base case. Like I said, that's extremely important because we're going to need to know that we want to get to this place eventually. We want to use that in our code, right? This is our recursive step. And then you don't really need to care about this for all integers greater than 1 because at the end of the day, they give us the base case, which means we know that this is only going to recur itself greater than 1. Yep.
So what do they mean by a type big O?
That is just verbiage of saying you need to. You remember how way back Leo was talking about dropping off all of the unnecessary terms? Like we would drop off the leading 5 or drop off the plus n. For these type of problems, they actually, when they say tight, they mean they want the actual answer. So for example, if this is going to give you 2n squared plus 5, the big O is just n squared, right? But the tight big O is 2n squared plus 5. Does that make sense? Here, let me go ahead and go back to what I'm talking about.
They don't want the highest order, they want like
They want the whole thing as it comes, right? That's how it is. They don't want any modifications to it. So like, yeah, as Leo said way back here, right? This is going to end up being n squared because we drop all the terms and we drop all the insignificant ones. You're going to learn in CS2 that this is actually called a loose bound. They don't ever tell you that, but what's the inverse of a loose bound? It's a tight bound. So the tight bound O notation here would be 4n squared plus 3n minus 5, right? Because it's more specific. We don't drop any terms. It's exact, right? So that being, actually, I can just go back over here. Okay, so that's what the tight bound is. For all of your recurrence problems, actually not all of them. There's one where they did. I'd say 80% of them, they're going to want the tight bound. If they don't say it, you can try to be ballsy and put the loose bound and just be like, oh yeah, I'm going to estimate with this final equation. But I would recommend showing your work for the tight bound because you'd rather be over specific than under specific and lose points, right?
Yeah.
All right, so what I always like to do with these, I need to see how much space I'm working with. We added more white at the bottom, so we have more room this time. I'm proud of us for that. We made some adjustments. What I always like to do for these type of things is on the right hand or left hand side, I don't know if that changes if you're whatever, just preference. I always like to make a chart for iterations, and I even like to show them, like write it down so that they know I have done my 2 iterations, okay? They don't have to go hunting for it. You want to make your partial credit come as easy as possible, right?
So do we do 2 or 3?
2 for all the partial.
Okay.
Yeah, I recommend 3, but 2 by minimum to get all the partial, right? And so we're going to consider this our 0th iteration, right? So iteration 0 is going to be 2t n over 2 plus 1, right? This looks weird. This is meant to be a parentheses. Okay. So to perform our next iteration, and I don't do the math on this right side, I just leave them there so they can find them easily. What you're going to want to do, right? So this is for t of n. Now, if we were to pass n over 2 into this function, so you're going to pass whatever parameter is here into itself. So that sounds a little confusing, but here's basically what I'll mean, right? So if we pass n over 2 into t of n, so this is our first iteration, so t of n over 2 now, right? What is that actually going to equal? So we know that that's going to end up being 2t n over 2, which is essentially n over 4, plus 1, right? But the thing is, we need to move that back into t of n. So what you do is look, so, okay, hold on. This is how you explain it. So this right here is what t of n over 2 equals, right? We follow that. So what we do is, whenever we want to complete an iteration, we have to express it in terms of t of n. We don't want t of n over 2. So what we can do now is, I'm going to erase this so I can draw my arrows, but remember that this in the box is Tn over 2. Where else do we see that? Right here. So this is T of n over 2. Right? You remember that. This is T of n over 2. And so if we want T of n is actually just 2 of T of n over 2, which is this. So 2T n over 4 plus 1, go up here, plus 1, right? And so this is actually our iteration 1. Every iteration is a step of you plugging it into itself, right? So now we're going to simplify this, and I'm going to write it on the right here, because remember, we want to keep track of our iterations. So 4t, because we distribute this 2 here, n over 4. Sorry if that change of colors messes with your brain. We go over here, and that's going to be plus 2, because we distribute that, plus 1, so I'm just going to update this to a 3. And that's this one doesn't count as our 2 iterations, so this is our first iteration, essentially. So we're going to do that same thing again, right? We now know what t of n over 4 is, and so what we want to do, again, is plug itself back in. So t of n over 4, where is it? Let me refresh myself. Right, so we're going to plug it into itself again. So now we want t of, wait, let me erase all of this. You guys remember the work for this iteration, right? You kind of understand how it worked? Because I'm going to use this space for the next one. So now we come back up here to this top equation again, and now we want what this value is, what t of n over 4 is. So if we plug t of n over 4, it's actually going to equal t, or 2t n over 8 plus 1, right? And then again, we want to solve for that, or no, t of n over 4, sorry, apologies, because n over 4 is a parameter here, right? T of n over 4. And so, I'm lying. Yeah, it's still over 8. It's over 8. And so the logic for that is we know what t of n over 4 is, right? So we go over here, and we grab what t of n over 4 is, and we pass in n over 8 as that parameter into itself. Because we just found that t n over 4 equals this. So we're going to take this equation, which is 4t n over 4, but remember, t of n over 4, t of n over 4. So we're going to pass 2, or here. So that's 4, and we're multiplying this whole thing by 4t n over 4. Well, no, n over 8, apologies. Plus 3 plus 1. Let me make sure I'm doing that right. No, plus 1. We're not pulling this part in. Plus 1. And this should still be 2. Awesome. So the reason we're pulling this in is because this is what t of n over 4 is. This is what t of n over 4 is. So we're just plugging that in for t of n over 4 right here. Sorry about that. And then that's going to simplify us to 8t n over 8 plus 4 times 1. And then this should be 3 out here, because the 3 comes from over here. And this is going to be plus 7, right? So let me erase all of this room over here. There's going to be 8t n over 8 plus 7. So we've done our 2 iterations for our extra credit. Is anyone able to determine what the pattern is here? If we could express that in terms of k.
Yeah.
What's up?
Yeah, so it's you're just multiplying it by the 2 to the power of k every single time, every iteration.
Yep. And actually, hold on. This should be iteration 1, not 0. Apologies.
So like 2 to the first is 2.
Yeah.
2 to the
So this first term could be represented as 2 to the k.
Yep.
Because we're starting at 1, so 2 to the power of 1 is 2.
Gotcha.
And then we have t, n over. And so again, in the first term it's 2, in the second term it's 4, in the third term it's 8. So by each step, we're dividing by 2 to the k. And then what's the n term? Someone else.
Yeah, in parentheses 2 to the power of k, and then minus 1.
Awesome. Is there another, because when I did this problem first, I got tripped up. Isn't there another type of series that goes 1, 3, 7 at the start? I don't fully remember, but that's what threw me off. So good. You guys, what is that? Something like that, yeah. So this is our k term, right? And because this is also worth extra credit, which we want all of, I tend to put it in the iterations table and say this is k. Oh. Right? So now at this point we have a lot of partial credit racking up here. I'm feeling pretty nice, feeling pretty confident about this problem. But we're not done just yet. So we're gonna have to go back here. And now that we have our kth iteration, right? We want to solve this right here. We want to be t of 1. Why do we want it to be t of 1?
That's what it says on top.
Because then we have a base case and we're not iterating to, however long, right? That's we're good, we're done, we can stop. And we want to do that because we want to use algebra to find out that position when we stop. So in order to get that to be t of 1, we're going to have to set n of 2 to the k equal to 1. So as we saw before, we're going to multiply this, so n equals 2 to the k, right? And then solving for k, we're going to get, that should be n, right? Hold on one second. Let me see what they did here. Like I said, this fell into my lap. I apologize for me having to reference all the time. Oh, actually, so here's the thing with this one. Sometimes in your problems, it's actually going to be good for you to simplify. Other times, it's not. So what I mean by that is if you come over here to the right, we see 2 to the k occur a lot. If we really wanted to, we could also say that this is log 2 to the n equals k. We could do it both ways. I'm actually going to go ahead and show it both ways. So we could do it this way. And then we take this formula over here. If you do, so this right here, right? 2 to the log 2 of n, what does that equal? That's just n, right? So in this case, we'll proceed forward with this. I'm doing it in a different way than the book, or than the solutions. So we've solved for k at that particular point. And if we take this formula over here and move it over, that's going to be 2 to the log 2 of n t.
Yeah, it's not showing.
Uh-oh. I'm moving it on my side. There you go. Wi-Fi issue. All right. So log 2 to the n t, and that's going to be n over 2 to the log 2 of n plus 2 log 2 to the n minus 1. So let's go ahead and use some algebra to simplify this. We know that anything to the power of log itself is basically just like, we can cross this out, right? We don't need to worry about that. So this is actually going to simplify to n t. Same thing with this, log 2 to the power of log 2 cancels out. So we're left with n over n, and any number over itself is just 1. So we could simplify this to 1 plus, and this is going to be, again, these cancel out. We have plus n minus 1, right? And what do we know that t of 1 is? We go up here, the base case is 1. And so this is that missing piece we would like. We want to just get rid of t and just boom. So now if we go ahead and simplify this, that's going to be 2n minus 1. And so that is our type bound right here. Question? Okay, so because if we come here to our kth iteration, you see this term right in here? So we want the term that keeps getting passed into t, we want whatever that is to equal 1. So if I come over here, this is where I derived it. So I have n over 2 to the k equals 1. Because remember, we want this to the right here, we want that to equal 1. So we can utilize the base case. So essentially, we multiply the 2 to the k over, and then we solve for k. And this turns log 2 to the n equals k. Because if we know the value of k, we can then come back to this equation and plug it in for every instance of k, which is what I did right here. If you look at it, the first term is 2 to the k, so I did 2 log 2 to the n. The internal is n over 2 to the k, so it's n over log 2 of n, right? See all of this? And then when you plug that factor, whatever k is, when it is 1, into all of these, you're left with the base case right here, which we can then replace with the value that we need from our base case. Does that make sense? Any questions? So just as a reminder, we can kind of see where we did this. Where am I? Okay. So we come over here, right? We perform 3 iterations. We perform 2. Right here. Right? We did our 2 iterations. We found the pattern, right? Step 2, express the iteration in terms of k, where k is the kth iteration. So we expressed it down here, right? 2 to the kt, n over 2 to the k, plus 2k minus 1, right? You see that we've expressed it. And then we solved k equal to 1, or the internal term, the argument, right? Equal to 1, right here, this step. And so notice that I'll show the solution. And this is the fun part of math, or maybe not fun if you're not into math like that. But as you can see here, they actually solved. This is a different solution. Hello?
Yeah, the solution was the one before.
Well, it doesn't look like the solution's updated, because that's not the same one. Well, I have it here. This is evil. All right. I wish I could get the partial credit breakdown for this, because it seems like it didn't update on my iPad. Maybe I didn't refresh or something. We changed the slides right before this. Here, I have it up on the other screen. So I'll tell you the partial credit breakdown for this. You get 2 points for this iteration right here. What's up? Oh. You get 2 points for that iteration right here, this one. You're going to get 2 points for this iteration. So we're at 4 points right now. You're going to get another 2 points just for expressing it in terms of k, right? So right now we have 6 points without even coming to the type bound. You get another 1 point for solving for k, which is right here. We remember solving for k. And then another 3 points for finding the type bound notation, which is 2 of n minus 1. Questions? All good? Yes.
So for the iteration number, you start with 1 for the provided.
Yeah, because, see, remember how I said at the very beginning we don't actually care about this? Well, I'm stupid and I'm dumb. This is them telling us that we're starting at 1, essentially. Yeah. All good? Good to go on to the next one? All right, I'm a little worried for evil recurrence too, y'all. I don't know about you guys, but...
This doesn't look that hard.
Well, I think evil recurrence 2 is where things get bad.
Okay.
So... I heard it. So I'm gonna have to reference my thing a little more. I'm gonna be transparent about it, but I will be able to explain it once I sort of understand it, right? there are some cases within your recurrence relations where, if you remember this term to the right, we ended up getting it was 1 plus 3 plus 7. What's the next term in this case? 15, 31, because it's 2 to the n minus 1, right? Sometimes that little case at the end is not going to be that nice. And you will need to use summations in recurrence, right? So everything ties into each other. So let me go ahead and kind of show this here. This thing's a mess, and I'll sort of go into why. So we're going to do the same thing. What time is it? 4:47. We're doing all right. We're going to make our iterations chart again. And now this time, we're starting at 0, right? So now I know, right? This is the 0th iteration. So iteration 0, we're going to write it as is. 4t n minus 1 plus 2 to the n, right? We're going to start doing our next iteration. So t of n minus 1 equals 4t n minus 2 plus 2 to the n. And we know that we know what t of n minus 1 is from over here. So we're going to plug that in. That's going to be 4, and then this value right here. So it's going to be 4 times 4t n minus 1 plus 2n plus 2 to the n. Just making sure I'm not crazy. Oh, and this actually should be, hold on, I'm blanking. Forgot how to iterate. Right. This is where we're going to apply the n minus 2, the internal part right here. Sorry about that. So it's going to be, in this case, it's going to be n minus 2 and then n minus 1, right? You see where I kind of got that from? Because this term is now n minus 1 from here. We're going down. Are we going down? Yeah, we are. This is going to value out to the Zoom? Oh, yeah, no. I'm not recording my audio on the Meet because I don't want it to play out my iPad and then play into my laptop and then play on my iPad and play on my laptop. We're going to get that weird feedback. I promise. Yeah, y'all see my mic bar moving. We've got audio. We're good. All right, you scared the living hell out of me. Okay. All right, so the next thing we're going to do, we're going to evaluate that. The second iteration is going to be 16t, and this is where we're going to start seeing the weird pattern that I'm talking about here. So n minus 2, we're going to distribute that 4 into 2n minus 1, right? But if you think about it, applying, so like 4 is the same thing as 2 to the 2. Do we all agree on that? Yeah. So when you multiply this onto this, you're actually getting, because of exponent rules, if you multiply two things with the same base, you can add their exponents, right? So we're getting this right here is going to be 2 to the 2 times 2 to the n minus 1. Does anyone know what this is going to give me? Because we're going to add 1 to it, so then it's going to become 2 to the n. And then we're going to add another to it, and it'll be 2 to the n plus 1. So that's what we get here. But then we're going to add that to this. So we actually have 2 to the n plus 1 plus 2 to the n. Right? You guys see that because we're bringing this over from the outside. So plus 2 to the n plus 1 plus 2 to the n. Right? Y'all see that? Y'all see how we got that? Right? And because we're not multiplying or dividing, there's no simplification we can do for that addition. We're just going to have to leave it as is. All right? And so again, we're going to do the same iteration. I'm going to save a lot of that annoying math. You can kind of see the pattern start to come out. So this is going to get multiplied by 4 again. It's going to be 64t n minus what? 3 plus, what's that going to be? So let's do the math for that. So we're going to end up having 4 4, again, apply it to 2 to the n minus 3. The reason that it's n minus 3 is because this is the n minus 3th term. And that's going to be 2 to the n minus 1. So now it's going to be 2 to the n plus 1 plus 2 to the n plus 2 to the n minus 1. I believe I did something wrong. It should be a plus. Sorry about that. We're adding on to that, not subtracting. So this should be, let me see. It'll be 2 to the n plus 2, then plus 1. Right? And so you can kind of see this pattern that we're creating here. So what is this going to be? So are you for real? I think my iPad just died. No, we're good. All right. So we're on our kth iteration now, right? How are we going to express this in terms of k? The first part is like relatively straightforward. We can kind of see it, right? So remember that this is the 0th iteration. So the kth term is going to be 4 to the k. I'm tripping again. This is supposed to be iteration 1. So I think you always start with 1. My bad. So this is always going to be your first iteration right here. But we're going to express this as 4 to the k. And so in this case, it should be n minus k for the internal, right? Because we're always subtracting. So on the first iteration, we're subtracting 1. On the second, 2. On the third, 3. But then what is this going to be here on the right? This is the fugly part. This is what I was talking about, right? Oh, this can't be that bad, right? This is going to be a summation. Because if you think about it, if you look at the right, we're continuously adding terms with a parameter that's based on the input, right? We're going up to a specific point. So this is actually going to be the summation. Does anyone want to try to tell me what the bounds for the summation are? Up to k minus 1. So in the case of k equals 3, the summation is actually going up to 2, right? So we know that it's always going to be 1 less than our kth iteration. The way we also know that is our first iteration, we're at essentially 0, right? We're at n to the n plus 0, right? We're not worried about that. So then the internal component of this is going to be 2 to the n plus I. Does everyone see how we got that summation on the right? Because we're adding 2 to the n plus 0, 2 to the n plus 1, plus 2, so on and so forth, right? And so this is going to be fun. And by fun, I mean terrible. So let me go ahead and erase all this. And then I can leave this god-awful math alone. Let it rest. Sorry for the very long erasure. I have a lot of writing up here. Okay. So what's our next step in this, just generally speaking? Question?
Is there a T in front of the 14K?
Yeah, sorry about that. That's the function, yeah. So what's the general next step here? We're going to want to do what? We're going to need to solve for when n minus k, because it's that internal component, equals the base case, which in this case is 0. So thankfully they gave us a pretty straightforward what's up?
I think you might have made a mistake because every iteration we're multiplying it by 4, right? And a 4 is 2 to the 2. You're putting it like n plus 1 instead of n plus 2. Shouldn't it be increasing by plus 2 every iteration? Like that there?
Well, yes, but also we're adding 2 to it, but every time we iterate, we're also decreasing the exponent by 1. Because you see how each time we iterate, we're at n minus 1, n minus 2, n minus 3? And that's eventually what the exponent n is. So we're applying 2 from the 4 every time, but we're also subtracting 1 because the parameter decreases by 1 every time. So it is by 1, yeah. Good question. So again, we're going to solve for this. Thankfully, it's pretty straightforward. N is just going to equal k, right? Or k equals n. And so now we're going to take this general form, and we're going to plug all this in. So 4 to the n, right? We already know that when we plug in for this, n minus n is what? it's 0, so we could just go ahead and plug in 0 equals 1, and we know anything times 1 is just itself, so I'm just going to leave this as 4 to the n, right? And then the right-hand side, we're going to do plus the sum of I equals 0 to n minus 1. The reason it's n, we plugged in k, all good. We have 2 to the still n plus I. What's up? So the same thing as the last one. It's the internal parameter of the kth iteration.
Okay.
So yeah, again, we want to solve that equal to whatever the base case is going to be. So imagine that t of 1 equaled 1. Instead of solving this for 0, we're going to solve it to 1. Because we want that internal component to be what the base case's internal component is so we can simplify. All right, yeah. So, yeah.
So, because earlier we turned 4 into 2 and 2, so is there like a reason we turn it back into 4? Is that just easier to?
So in the next step, I'm going to turn it back. It's going to be easier to work with everything in 2s. I was just taking it straight from this. So I'm going to start doing that sort of algebra. Really, at the end of the day, they equal the same thing. So it really doesn't matter. But when we start factoring things out, we're going to want it in 2 to the n plus 1, right? Which actually, I'll go ahead and do right now. So just to prove that math to you guys, 4 to the n is the same thing as 2 to the 2 to the n, which is just 2 to the 2n, if I recall correctly. Yeah, that simplification, 1 second. Yeah, 2 to the 2n, right? So we're good. So I'm going to make that 2 to the 2n. If you have something with an exponent, like 2 exponents, you can actually multiply them together. That's another exponent rule. Now the hard part's going to be what's on the right. How do you guys think that we're going to go about this, right? We need to start, first things first, we need to get rid of that internal 2 to the n because we can't work with that. That's just not something we can work with. So again, what did I say about exponent rules? This is a neat little trick. If I have 2 to the a times 2 to the b, that's really just 2 to the a plus b, right? Can we all agree on that? So if we think about it, we have 2 to the n and 2 to the I, which means we have this, right? We agree that that is the same thing as this. All in agreement on that? So what we can do here, if you remember the summation rules, if we had the sum of, like, forget the parameters, it doesn't matter, but 5c, that actually equals 5 times the summation up to c. You guys remember that rule? We're able to pull out multiplications inside of this summation. So we're going to take n out here, and we're going to move it outside, right? Because, again, we're getting rid of this constant factor. Why do we want to move n outside? Why is that something important? Summations are in terms of I. You can think of it as a function, right? N is not any type of input on that function. If you really think about it, in terms of the loop that is the summation, n is a constant. So we're just going to take it out so we don't have to deal with it. So now we're left with this, right? We have that up to 2 to the I. Everything's looking good. Another thing that we can do is we're going to be able to factor this a little differently. So let's move this back to here. That is the same thing as 2 to the n times 2 to the n, right? Because it was 2n, so we can kind of break that apart. And if you see here, these two terms are the same. So I'm just going to factor that out. Less to deal with. So it's going to be 2 to the n See how we did that, right? Everyone in agreement? We pulled 2 to the n out of both of those terms. So we just moved them outside. And now from here, what we're going to do, I believe we're going to perform a shift to make this a little nicer to work with. Yeah, we can take the, trying to see what they did here. I believe what they do in this case now is they want to make this go up to n so we can have a summation that we can work with. And by doing that, I had to explain this last year and I struggled. You could imagine when you're taking you're moving it up one, so you're moving a term out. Here, let's try to explain it this way. So let's say we have 2 to the 0 plus 2 to the 1 plus 2 to the 2. That's from 0 up until n would be 2. If we take this out and this becomes 1, we would then have that summation with 2 to the 2 outside. What we're trying to do is we're trying to pull out one of the terms to make the thing work for us. So we're going to pull one of them out, and that should be, I don't remember what term that's going to end up being. It should just be 2 to the n minus 1. Yeah, so 2 to the n minus 1. And in here, this cancels out. I don't know how they actually get that to cancel out that way. One moment. I'm going to stop. If anyone in the audience wants to help me out here, I'm kind of stuck. So, what's up? Say that again? If we didn't factor out the extra 2 to the I, so we can move this back. Hold on. So what formula did you say to use? Gotcha. I plus 1. So this is a geometric series. What's up?
Yeah, I was gonna say, is it a geometric series?
It is a geometric series, but I'm pretty sure geometric series needed to go up to n.
Well, I think it's n instead of I for the formula.
N instead of I for the... Oh, you're so right. That's what it is. Right here? Yeah. No. It has to be in terms of I.
I mean for the right side, right? It's like x to the n plus 1 minus 1.
Right. Because that's what the I term's going up to. So I'm trying to figure out how this... I'm just going to pull up the solution. I'm sorry that we're fumbling the math part here, but I wasn't prepped for this, and Leo just found out his class takes attendance, so he had to fly. So I'm going to try to show you what I'm talking about here, what they did. So we made it up to this point. Notice how they shifted the top index up 1, and for whatever reason, this disappears. I actually have no idea how they did that, or what they pulled out, but I know that once we get it into this form, whatever odd algebra trick they just did there, we're actually able to evaluate for that same formula that we were talking about, the x to the n plus 1 minus I over x minus 1. That would be this, assuming that the top bound is I. Does anyone have any theories on how they pulled out the upper bound and got rid of this? That means they probably subtracted by 2 to the n. They didn't shift the lower bound. They just pulled out one of the terms. Yeah, I'm not quite sure how they did that, how they got rid of this. But like once we figure that out, the rest is pretty straightforward. It's just this one step that I'm not sure how they got there. We would then be able to evaluate, plug in the formula for geometric series, and just multiply through, and then this is our type bound. So this is how we get there. Does anyone have any theories on how pulling out the upper term gets rid of this? I'm going to go ahead and go back. What's up?
I think it's that it shifts the upper bound of that series by the n, right? Because it's in the sub.
There you go. Okay, since this is going, okay, thank you. So I'm going to go back to the screen and explain this. You're right. So if we think about this, right, remember, very good catch. You're going to get a great grade. Anyways, so come over here. This 2 to the n, if you think about it, remember, a summation is just a bunch of numbers summed up. We're moving this 2 to the n into this, right? So this would be 2 to the 0 plus 2 to the 1. Let's say n is 5. It's going to go all the way up to 4, right? So dot, dot, dot plus 2 to the 4. But if n is 5, we have that term right here and can just put it into this summation right here. You guys kind of get how that happened? Or do I need to go through it one more time? So I guess my tip for that would be, if you see something being added to a summation and you're kind of stuck, think about how you could put it into the summation, because at the end of the day, you can consider the addition operator onto a summation. If it's the same shape and term, you can just put it in the summation, right? So that's how they shifted those bounds. Do we get this explanation right here? Again, I'm really sorry that I wasn't able to pick that up myself. Any questions? All good. Okay, so now we can, I'm going to not refer to the answer now that we've gotten to this point. So we're able to go back over here, and we can remove that and have that bound right here, right? Remember how we did that? We added that in. So this summation, we know, is one of the geometric sequences that we can do. So if I go back here, and again, this will be on your formula sheet. So your geometric series for a finite formula, I'm going to write it down really quickly on the screen over here so I don't have to keep toggling. It's A1, 1 minus r to the n, 1 minus r. All right. So in this case, the position of A1 is going to be 2 to the n. Here, let me move this over. We're going to try converting this. It's going to be, put this over here. The bottom 1 minus r should be, it's going to end up being 2 minus 1. I'm trying to figure out where this came, how we have this here. It's going to end up equaling 2 to the n plus 1 minus 1 over 2 minus 1. So we got that because 1 minus r to the n. This is in the form for an equation a to the r by n. So r in this case equals 2, n equals, for going up to I here, that should equal, hold on, let me refer to the slides again. A times r to the n. It doesn't mention where the upper bounds comes in, so we can do the maximum. So it would be n. And then a of 1 is going to be 2 to the 0, right? Because our first term is 0. So this should just be 1. So we have 1 minus 2 to the n. But we're able to change that around to the top factor. And then from here, we're able to simplify to, since 2 minus 1 is just 1, we can get rid of that. And then factor this through, so that should be 2 n plus n, so 2n plus 1 minus 1. This is our big O type bound. What's up?
If you use the one on the formula sheet, it's like 8 times easier.
Yeah? Is it a different one on the formula sheet?
It's the same thing. It's just, look at it.
Where?
On the actual formula sheet, so go back, where all the formulas are. Another slide. Another. See the one at the end? It's that. Just use 2 as x, because it's a constant.
Where is it?
The last one.
This one?
Yeah.
Oh, this is so much easier.
Yeah.
Yeah, and then they flip it. Okay. So that's how we got to there. Again, I'm sorry about that. So, any questions? What's up?
So is the like the general case one, if you have a summation
You should always plug K in before you start handling it. Yeah, you should plug K in first. All good? Yeah, they. I don't know what the hell this is. Yeah, we can't use this. Absolute value is not less than 1. I'll try to come up with some clarifications for Friday. I'm sorry I can't answer that. That kind of fell into my lap. So I'll do my best. I really apologize. For the sake of time and actually trying to give you all some more good information that I'm prepared for, we'll move straight on into binary trees. Question? I don't have an example, but my best advice for deriving the recurrence from a piece of code is you're going to want to find the base case and the recursive case. So that's how you're going to be able to derive this. So example, if the base case is if n equals 0, return 1, then that's what this is going to end up being. It's kind of looking at a piece of recursive code and trying to translate it into a form like this, and then from there you can start doing the recurrence. So that depends on the upper bound. So that's very similar to this problem. So no matter what's going on in here, imagine let's just say it's adding something. It's going to end up going to n because of the bound on the loop. There is no summation that you need to do because at the end of the day, it's always going to go up to n. If it was doing this is an example where it's doing something else, it's dividing by 2 every time. That's why the outcome is not O of n, it's O of n log n, or log n. Yeah. All right. I'm going to reel it back in. Question? Sorry, man. All right. I'm going to move on to binary trees. Everybody good with that? Yes. All right, awesome. Sorry about that again. So, binary trees. Something that we forgot to mention on Tuesday's lecture, something that I kind of want to tell you because it's something that's been asked before. How many of you know the difference between a data type and an abstract data type? Okay. Good. So I just want to take it back super quickly to Tuesday, or just in general, we were talking about stacks and queues, right? Even though stacks and queues are implemented the exact same way with an array or a linked list, which is their data type, the abstract data type comes from the fact that it will change depending on how you use it and how the user defines it should be used. I'm going to explain that more when we get to AVL trees, but I kind of want that to simmer while we go through binary search trees, okay? I'll bring that back up when we get to AVLs. So, binary tree versus binary search tree. First things first, whatever a binary tree is. So a binary tree, imagine a linked list, which we went over. You have nodes and you have pointers. But instead of one pointer to the next node, you have 2 pointers to its 2 children, right? Makes sense? So it's 1 node, 2 children, and that's where the term binary comes from. Now you could have n-ary trees that have multiple children. We're not going to get into that here, and you actually get into that in CS2. Have fun with that. But binary trees are a lot nicer because there's just 2 children. So the biggest difference now is the difference between a binary tree and a binary search tree. And so again, this is where that sort of abstract comes from. Binary trees and binary search trees, code-wise, the structures you use are the exact same. But the only difference for a binary search tree is the abstract idea that the left child must always be less than the current node, and the right child must always be bigger. For every single node in the tree, top to bottom, all of them. So that's the abstract data type of a binary search tree, right? Don't bother with that big block of text. I copied these slides from last year. I could probably explain this verbally a little better, but just to recompass everything I've said, right? Binary tree. And so, does anyone know why we came up with binary search trees? What's the whole reason that we want a binary search tree? Faster searching. And the reason is if we get really unlucky with a binary tree and we insert, this, that, and the other, you could have a binary tree that's essentially just a linked list. Only the right values, only the left values, whatever. And with normal binary trees as well, there's no sort of ordering. So we can't search in an effective manner. So binary search trees were introduced as an abstract data type to help get our runtime for all of these operations a bit better, particularly searching, right? Because if you think about it, if we have that property of everything to the left is smaller and everything to the right is bigger, every time you go left, you're dividing the amount of nodes you need to visit in half. Because if you think about it, on average, right? And so what does that mean? At every step, we're dividing by 2. And as mentioned, what type of runtime behavior is that? Logarithmic, which is significantly better than O of n. Because for something that's O of n, I believe, 5 million values could equal down to like 29 or something crazy in a logarithmic statement. My magnitude's probably off, but that's a big difference, right? And so we want to have that efficiency. So don't read these two bottom and top one yet. The biggest thing I want to talk about are some of the properties for binary trees, and I should have examples on the next slide. If not, I'll just look them up. So for a binary tree, actually I know what I'll do. I'll pull them up on the iPad. 1 second. So, full binary tree, you need to know all of these different terms. You need to know the height, the depth, full, complete, because there are for binary trees, you can get like a multiple choice problem or a true or false. Is this tree full? Is this tree complete? Yada, 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 right? So a full binary tree, every node that isn't a leaf has 2 children. I like to think of this as each node is full of children, right? There are no more spaces to put new children in all of the nodes except for the leaf. So an example of a full binary tree could be, this is the very straightforward one, right? Because these 2 are leaves, we don't care about those, right? This one has 2 out of 2 children. So now if I were to go like this, we're no longer a full binary tree. The reason is this one has another slot for a child. We put this here. This is a full binary tree. And what may confuse you, and that introduces the idea of completeness, this is actually a full binary tree. Doesn't look full, at least by the way we would think about it. The fullness is for each node, not for the tree entirely. So this is a full binary tree. We satisfy the property that all nodes except leaf have 2 children. Now if we want a complete binary tree, that's a different story. A complete binary tree means each of our levels are completely full left to right. So complete is essentially what you'd imagine as a full in the context of the entire binary tree, not just a specific node. So this is a full binary tree. This is a full binary tree. Can someone tell me, I meant complete those last 2 times. I'm so sorry. Can someone tell me if this is a complete binary tree?
Yes.
The answer is yes. So that's the caveat. A trick question. All the levels of the tree are completely full but the last. So the same way that for full, we exclude the leaf nodes, in complete, we exclude the last level, right? So this is a complete tree, this is a complete tree, still a complete tree, even though this one has 1 spot and this one has 2. Does everyone understand the difference between complete and full? I don't believe it has to be, but in terms of heaps, that's probably what you're thinking about, it will have to be left to right in order to maintain a heap property. So this is complete binary search tree, and a tree in general, it's a complete tree. But for heaps, you do need to have it be left to right. So don't let that confuse you. And I think they've done that as a trick question before. They've given this tree and asked you if it's complete, and the answer is yes. If it was a heap, then you'd be violating the heap properties. But that's something we're going to go over tomorrow. So I'm going to get rid of all of this. I'm stupid. I should have kept that. Okay, let's do this again. I'm going to draw us a sample tree. I'll do here, 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 here. All right, the next term that we want to go over is the difference between height and depth. they are kind of like inverses of one another. They pretty much are that, right? So for a height, it's the number of edges. That's a lie. That's the depth. Again, didn't make these slides. And the height is also known. No, it's not. Binary tree. I'll explain it in my terms then. The height, it's backwards. All of the lowest leaf is going to be 0. So this right here, this node has a height of 0. The next one above it, all of these nodes, this has a height of 1. This is a height of 2. And this is a height of 3. So the node is gonna, or the root node is gonna have the highest height because it has the most edges underneath it. The other way you can check height is counting the number of edges from the root. So this is 1, 2, 3, or from the bottom. So this right here, height of 3, right? Depth, however, is the opposite. Depth is how many times you're gonna need to traverse in order to get down to that node. So in this case, your root is going to have a depth of 0 because you're not traversing down at all to go there. So these two will have a depth of 1, these will have a depth of 2, and this will have a depth of 3, right? So you can imagine you're placing a binary tree, if we had one in real life, onto a table. The height is how high up it is. Makes sense. The depth is how far deep you have to go. And so that's how you can kind of distinguish those two. I like to think of depth as down. It increments as you go down. Depth is down. Right. Awesome. And again, I don't have any good one for height, so you just have to remember one and you know the other. Okay. So in a balance, like I said, in a balanced binary tree, or no, okay. So this is a different thing. So this isn't talking about the actual search properties of the binary tree. In terms of balancing, we want the height of the left and right subtree to differ by at most 1. So what does that mean? And we're going to go over the same syntax with AVLs, right? Right here, the depth of its left is 1, 2, 3, right? So its left is 3 deep, and its right is 1, 2. So the right is 2. And we can talk about this as the balance factor. So the balance factor here is 1. A balanced binary tree, the difference is at most 1. So this is a balanced binary tree. And now why do we care about balanced? Because this is the factor that is going to help us maintain that logarithmic runtime I was talking about. Because let's say in a binary tree I inserted 1, 2, that's so backwards. 2, 3, 4. While this is still a valid BST, this is not balanced at all. And so now the problem you're going to have to deal with, and which we'll talk about in the next section after I do these example problems, is we need to figure out how to keep things balanced. And so you have one solution called an AVL tree, which we'll go over next. But CS2 is all about that. You're going to go over like 4 different trees for keeping your binary search tree balanced. And they all suck so much worse than AVL. Prepare yourselves. So the other thing that we want to talk about for binary trees is traversal. Right? So there are 3 types of traversals for a binary tree. There's post order, in order, and pre-order. So the way I like to think of it is this. Right and left will never be swapped. Left will never come before right. Or no, backwards, left, right. Left will never be after right. So sorry. And so what these prefix terms are, pre, in, and post, is where the root's going to go. So I'm going to label the root as T because I don't want to have 2 R's, right? So for pre-order, the root is printed first. It's pre. In order, the root is in between. In order. And post order, the root is printed last. Post, as in after, right? So those are all of like the big terms we need to know for binary trees. Question?
I like to think of it like on the problems where you have to like break it out like a pre in or post order. It's like you put like a node on the left side is the pre, on the right side is the post, like down is the in, and then start from the left and trace. And whenever you hit the
a snake, kind of. Yeah. Well, I think we actually have one of those problems, so we could go over that. Okay, and then here are properties of a binary search tree that pertain only to a binary search tree. That was just all the properties that apply to binary trees, but obviously they apply to BSTs as well. Biggest thing is left, lesser, right, greater. This is what I was saying, right? Having that property of the search becomes very easy. This is basically saying the same thing, right? It needs to maintain that property for the entire tree. And usually binary search trees will have no duplicate nodes. There are some special cases where you can handle those, but we haven't seen a duplicate node problem on the exams before. So just some examples. This is a valid binary search tree, and we know that because 6, 8 is greater than, 9 is greater than 8, 7 is less than 8, 4 is less than 6, 3 is less than 4, 5 is greater than. So we're all good, right? But not a valid binary search tree. So 8 is greater than 7, right? Why is this not a valid binary search tree? 6 is smaller than 7. So that property does not maintain for the entirety of the subtree underneath 7, right? So that's a trick, because keep in mind, when you do this, you need to look, when you get to those bottom levels, you need to look up as well, because 6 is less than 8. We can all agree on that, right? But you have to make sure that you look up and make sure you realize 7's come before it, all right? The best way to look for BST is actually to go left to right, looking at like an entire column. So like we could say 3 is less than 4 is less than 5 is less than 6, 7, 8, 9. Kind of see what I mean there? We read left to right, regardless of the height. That's another good way to check for a binary tree while looking at all levels at once. And then this is not a valid BST for the same reasons, right? And so we can come here. So again, this is kind of the same thing I was talking about with recursion, right? So pre-order, pretty straightforward to code and look at. We're printing the root first as we go down, then we go left, then we go right. Could you tell me what the order of the code would be if we did a post order?
Left, right, and then print.
Perfect. And so you could think about it again. If this was at the end, you only print the root after you've resolved its left and its right. So you print the roots on the way back up. I'm going to skim through these 3 here. Or actually, let's do one of these exercises. So this is in order traversal, right? This is in order traversal. So how would this be printed? So we know in order is going to be left, then root, then right. So we go all the way down to the left. We print 4. We go back up. We visit the root. We print the root. We hit the right. Print that. 5. Does anyone know what's going to be printed next? We print 1. And then we traverse the right.
This is in order, right?
Yep, because we printed the roots in order. So let's do the next exercise. I believe this is post order. So let's do post order. So again, let's remember, post order is left, right, root. So we're going to traverse down to the left first. What's the very first node we're going to print? 4. Then what? So 5. So we print the left and the right of this root. So then we can resolve it. So we 2. We haven't print the right side of this one yet. So we go all the way to the down. We go 6, 3, 1. 4, 5, 2, 6, 3, 1. Perfect. Oh, I think we went straight into problems. Okay. So I'll start doing this problem. Look who's back. Yeah.
Post order's left, right, root.
Yep. All right, so we're headed on to the problems now. So we're going to get a function called sum single parents. And essentially what we're trying to do is we're trying to find all of the different, write a function called sum single parents that takes a pointer to the root of a binary tree. And it's going to return the sum of all the values with nodes that have one child, or in the nodes with a single child. So in this case, 3 has one child, so it's 3. 8 has one child, so it's 5. 20 has one child, so we add, or no, we're not adding their children. Sorry about that. We're adding the actual number. So this would be 8 plus 20, and that's the only ones with single children. So this should feasibly return 31, as you can see here, right? So what is our very first base case we should always check for? We're going to check if root equals null. And what do we want to return here? This is a leaf. A leaf cannot be a single parent, so we're going to return 0. I need to start writing smaller. So what's the next thing we want to do? We want to check if we're currently at what? A single parent. First thing we want to do is we actually want to hold on to accumulator, because we're going to want to assign, we need to return the left and the right. So here, let me make this better. And so what we can do, yeah, you're right, we're going to check if it's a single parent. So if, and how do we check single parent?
If root left is null, and then root right has some not null, and then flip flop.
And then flip flop, yep. And I'm just going to write this to say, hey, we're doing both. Or, right, for the flip-flop, just because I run out of space really quickly. And so if we're currently at a position that, you know, left or right, we have a child, we're going to want to add to our sum the actual data at this specific plus root dot data, or arrow data, right? And so this way, we're at a position where we're going to add it. And then what we need to do is, after this, we need to traverse. So what we can do is we can do our num plus equals. And what are we going to do here?
Call it recursively.
We're going to call it recursively for the left. I'm just going to call it single. And then last but not least, it's an integer type. We can go, and I called this num. Let's call this sum. And we'll just return sum. And so if we the best part about a binary tree is, remember that recursive tree we drew? We could like draw it and it would make a binary tree, which is kind of cool. And we could just fill out what it would be at each of those specific positions. So what we could do is we could kind of trace it looking here. So we went left, not single parents, and then we'll traverse down 4 first. We'd go here. This if condition would be true. So we would put 3 plus. It would go down this way. 2 is going to be a child. It's going to end up being null, so it's going to be 3 plus 0. This is going to resolve to 3 plus whatever the right value is. So again, we go down here. We know 8 is a single parent, so it's 8. 5, it keeps going down until it's null, so it returns 0. So this is 8 plus 0. And then from here, we have this on this side, and then again on this side, we'll get 20 on this side, and it will return to be this at the very, very top. So do y'all see how we did that? So note, traversing a binary tree, you're always going to want to check if the root is null for the base case. And whatever you do for the right, you're probably going to want to do to the left. What's up?
What if the left though? What if there's only a left though?
I meant to put this, so this means like flip flop and or it. So like I didn't want to write the whole thing out.
Oh.
Yeah. So like imagine here as well we did if root right equals null and root left does not equal null. That's what I was doing by this. I just didn't have enough room. I'm about to start going off to the next one, right?
You're supposed to do like an or statement as well.
Yeah, you need to make sure that you do an or statement. Yeah.
I know my handwriting's really bad, but
What's up?
you check a null for one side, not null for the other, and you do the opposite. Do the or statement. It's all the same. Exactly. All
Yeah, you could return data plus single left plus single right. Which is gonna be like, you know, I didn't have enough room for all that. So But yeah, you can do it as long as it, you know, equals the same thing. You'll get the points for it. Awesome. So I guess we have more slides after my problem. I guess I'll pick up here. So yeah, let's talk about inserting and deleting in a binary tree, because that's something that comes up pretty often as well. When you're inserting, it's pretty straightforward. You're just going to keep going left or right until you find a null spot to insert the binary node, the tree node. So in this case, we want to insert 40. So we're currently here. We're going to check, is 40 less than or greater than 100? It's less than. So we go here. Is 40 greater than or less than 20? It's greater. We go here. Greater than, less than 30. Great, cool. 40 goes right here, right? And so ends up being placed right there, as expected. Cool. Any questions on binary tree insertion? Cool. And traversal, question?
Can you show the previous slide one time? Oh.
And traversal is the exact same thing. We're going to keep going node by node, going left or right, depending if the thing we're looking for is greater than or less than. And that's how we get that logarithmic property. So here's deletion. I feel like deletion is the one that has a little more people wrapped up, right? Because technically there's like 4 cases or whatever, blah, blah, blah. So if you're deleting a leaf, super straightforward. Just boom the leaf. Get it out. It's not going to affect anything. Everything's fine. So you want to delete 20. You get rid of it. If it has a single child, it's quite literally the same thing. Just boom it and move its one child up, right? So we're going to do that, and we delete it. 80 moves up, so that 80 ends up here, right? And so why is it only that case when there's one child? Because if it has 2 children, which one are we going to move up? How do we know, right? If we moved one of them up, then some of the values of the left tree might be greater than some of the values in the right tree. So it's this weird thing where we violate the whole binary search tree property. So again, this is both children. What you want to do, I wish there was a better example. There's not. So if there's both children, there's 2 approaches you can do. I think the FE assumes successor, so we'll go with that. So here, let's imagine, all right, this is 50. I'm writing over it so it doesn't look like it's like highlighted. And let's say we have, I'm trying to keep the valid BST here. Let me see if there's anything I can do. Actually, is this a... No, that's 60, not 50. Wait, are we... Oh, we're deleting 50. Never mind. This is a good example. I was lying. So we want to delete 50, right? And so what you can do, you can grab... Basically, the successor is going to be the very next greatest element. So grabbing a successor, you're going to go right one, and then left until you hit null. Why? Because remember, a binary search tree is increasing from left to right. So 20, 30, 40, 50, 60, 70, 80, right? Left to right. So if you want the next greater node, you need to go right one and then all the way down to the left. That's the successor. If I ask for the predecessor, what do you think we would do? We would go left one and then all the way down to the right. So since we're going all the way down, we know that it's going to end up being a leaf node, right? So what happens when we want to delete a leaf node? Easy peasy. Just get rid of it. So we find a successor. So we go all the way down to it says swap it. I just delete it and overwrite, but it's fine. You go down to the successor 60, you delete it, and then you move it back up here. And so we have 50's gone, 60's up here, valid binary search tree at every level, everything's good, right? Any questions about deletion? What's up?
Do we have to assume that it's going to be the successor, or can it be either one?
I've seen some problems where they'll draw both, whether you pick predecessor or successor. So I usually go successor, but assume either. You could do either. All right. So I already did some single. I don't know why it was thrown in the middle there, but we did that. I believe the solution, yeah, no, don't look at that. Here, that's some single parents. So if you remember, we set the sum, we did the null root check, we traversed left and right, we added it, returned the sum, right? See this right here. Many ways to do this. So like you asked, can we just add them together and return, like inline return that? Yep, everything's good there. So let's go back to assign heights. So this problem's fun. So we're given a struct for a binary tree, a binary tree node, and we're actually given a height as a parameter this time. This is going to be very helpful for this type of problem. But what they want us to do is they want us to assign the heights to each of those, right? So remember, can someone tell me the height of the root? Height of 3. What's the height of this guy down here? 0. So what is this telling us, right? We have to start from the bottom. How are we going to do that? So we need to do all of our processing on our way back up. Again, it's the kind of same mindset that I did for my little recursion lecture. So, well, here's what we're going to do. We have that question in mind. So we're going to traverse all the way down until we hit null, right? So we're going to say if root right? We're going to return. Because we don't want to assign any value to a non-leaf, right? It's fine. There's no leaf, there's no node there to even, work with. So we're going to traverse all the way down to the left. And why am I doing all of the logic after the recursive calls? Because we want to work from the bottom up. So we're going to go root left. We're going to go assign heights. We're going to go root right. And so what do we need to do here? We want to basically say we're going to be 1 greater than our children, right? Our height will be 1 greater than our children. So we need to think about how we want to do this for the case of a leaf. And then we're able to work our way back up for the bigger ones. So let me just draw something here. So let's say we're right here, right? So let's say we're on the very, very, very leaf node. We'll just say that, because what we want to do is on our way back up, we want to do 1 plus the height of our children, right? So what we can do actually to force 0 to be for the leaf, we could do int h equals -1, right? And then what we can do is, let me try to explain the thought process here. Because -1 so this is essentially what we're going to be returning here. Or we're not actually returning anything because this is just an assignment. So we're actually going to say root height equals this, right? We're not actually returning anything. It's a void function here. We just have this so that we can back out early. So we're going to assign that. So in the case of a leaf, we know that this is now going to give us, we're not going to update that -1 at all, and it's going to end up being, it's just going to end up being 0. So now, since we're working on our way back up, we can check the height of the left and right. So we're going to say the left height equals root left height if, I'm using a ternary here. This is kind of weird here. I'll change this so I don't have to explain what a ternary is. We're going to check if there even is a left node. So if root left, then we're going to say I'm setting a variable up here to hold the height of the left and the right. The reason we're going to do that is because eventually we're going to take this value right here and we're going to add the maximum of the left and right height, right? Because if you think about it, we're thinking about max here. Because the height of the left here is 2 and the height of the right equals 1. The height of this is going to be 3. So we need to figure out the height of the maximum one, right? So that's why I'm saying if there's a left one, we're going to say left equals root. This is an L, by the way. I'll make these capital. Left height. And then we're going to do the same thing if root right. We're going to say right equals root right height. I'm just going to put H on there. And then we're going to say our new height from our children is going to end up being max between our left and our right. Right? So in this case, let's say our left here is 2, our right here is 1, right? So we get the maximum between those, which is going to be 2. And then our height right here is that plus 1, right? And so that would end up resolving to 3. You guys see how we did that? So any questions here? What's up? Wait, is max not built in? It is a built-in function, no?
Yeah, it says no helper function, so I don't.
Well, you could do that. You could do that with a ternary. Yeah, you could do height equals L if L greater than right, else right. If y'all want to do that. I don't know how they do the maximum thing. Here, I think my solution differs from this actually.
So in the if root right, you can add and.
Oh yeah, and right is greater than left, and then just reassign. Okay, so that's something else you could do as well. So, do you want me to do that, or you guys kind of understand the concept? So here, let's go over here. Yeah, so that's what they did here. So, since max isn't a built-in function, and I'm Python brained as hell, you could basically, when you check for the right one, just if it's like if it exists, then we have to check if it's greater than, and if it is, we just change it. So they keep track of the biggest one, right? And so this is here. Big is the same thing as our h in our case, and instead of using a left-right variable, they just updated it as they went, right? Any questions? Sorry if mine's a little different. Any questions? So essentially, we're moving all the way down to the bottom of the tree, assigning the leaves to 0, and as we go back up, taking the greater of the two sub heights and adding 1 to that. Good? Awesome. And then this is num single parents. We already got into that. So I guess we'll move on to AVLs. You want to take it? Now that you're here? All right, cool. I'm going to hand it on back to Leo, and then I'll come back for sorting. It was all right. I need to just go to the bathroom. I'll do the AVL problems.
All right, sure.
All right.
You studied over them? Or?
Yeah.
All right. One sec. Let me put on the microphone. Seems like Dylan ditched it, but you know, I think I'll stick with it. Okay, so you all just went over binary search trees and binary trees, right? So let's go straight into AVLs. So what is an AVL? It's just a balance tree. That's all it is. So AVL, balance tree, and let's define a balance tree. A balance tree is such a tree where the height of its left children, or the height of the node at its left, differs no more than the height of the node of its right by 1. And I think there should be a slide in here that explains that, and I could kind of help you visualize that a bit more. But let's see what this one's saying. So this tree is AVL because of that rule. So let me explain it here. So the height of this on its right is going to be 2, and the height of it on its left is going to be 3. So it differs by 1. If it differed by more than 1, then you would have to do rotations. So AVLs are all about doing rotations so you balance the tree. So here it's good on this node. What about here? So the height on the left, it's 2. The height on the right, it's 1. Differs by no more than 1, so it's good. What about this node? Left, it's a height of 1. Right, there's nothing there. Differs by no more than 1, so it's good. And here, both height 0, so it's also good. So each of these nodes satisfy that condition, so that makes it AVL. So that AVL property or balanced property is really just each node having its left children and right children height differ by no more than 1. Okay. So let's look at something that's not balanced. So I think this is the same exact as the previous example. Yeah, I don't know why I switched the slides so many times. But let's look at this one. Let's see why it's not AVL. So instead of going from the top and kind of like breadth first searching downward, I'm going to start from the bottom. So 2, this is good. We know that its left is 0, height of 0, and its right is height of 0. Nothing to worry about. What about this 4? What is its left and what is its right height?
1 and 0.
1 and 0, yeah. Okay, what about this 5? Left height, right height?
2 and 1.
2 and 1. What about here? What about this 8? What? 3 and 1. So it differs by more than 1, therefore the tree is not balanced and it's not AVL. So AVL is kind of used interchangeably with the term balance, but it also refers to the algorithm of rotation. So when you say AVL, you assume balanced, and you assume to balance it, if you need to balance it, you would rotate. And I'll go over rotations in a moment. Oh, is there a question? Yeah.
Isn't the height of like the tree with no nodes -1?
Is it?
What's up?
Height of a tree with no nodes, -1.
No, I don't think so.
No. It's 0. I'm pretty sure. If somebody wants to fact check me, they can. Yeah.
I guess it could be like -1 -1.
Wait. What are you saying?
I have no idea.
It's okay. It happens. Okay, let's move on to the next one. So, okay, it's unbalanced. What do? We need to do rotations. That's the whole point of AVL. It's annoying to code, but they won't make you code an AVL. Wait, they won't make you code an AVL. They'll just make you do the
Don't
rotations.
scare them, they won't. There are always going to be tracing problems. All the AVL problems, that or like runtime problems, but you're never actually going to have to write a line of code.
Okay, so let's look at what a left rotation is, and hopefully I can explain it well. So right here we have A, B, C. We can see that at A, its right path has a height of 2, and its left path a height of 0. Differs by more than 1. What do? So we're going to do a left rotation on A. So what a left rotation consists of is grabbing the node to the right of our current node, so that's node B, and it's going to be pulled up to where A is, and then A is going to be now the left child of B, and if B had any children, okay, hold on, this should be a good explanation to draw. Okay, so if we do a left rotation on A, that means taking its right child and rotating it to the left. That's what that means. And what happens, as in this example, is that B gets pushed upward and its left child becomes what its parent used to be, which is A. So now B has a left child of A and a right child of C, and now you can see that we have an AVL tree as it's balanced. So B has its left child and right child of height of 1, or differs by nothing. Also, I think because someone mentioned -1, if you actually go to the left and right, this would be a height of 0, but still it's just like I'm adding an unnecessary 1 because it's simpler in my head to look at it from this node. But still, same result, it differs by 1. If it differs by more than 1, it's unbalanced. If it differs by at most 1, then you're good. One thing that I want to clarify, because I don't think some examples have it here, what would we do if B had another node here called D? Because now see, B has a left child and a right child. So where would this node D go? Any ideas? Oh, yeah. Left side or right side of it? Like this? Oh. Unfortunately, no. It's the other side of A, though.
D would become root, and then B and A would be the left children of D.
D wouldn't become root.
D would not become root. So here, I'll explain. So the rotation happens as normal. Pretend this doesn't exist until the end. So since B was the right child of A, now because A is moved down and it becomes the child of B, it no longer has a right child, right? And because of that, it has a free right child. So that's why we put D here. But it's not the only explanation. The other explanation is that you could see that D is actually the successor here. And I think Dylan covered that term previously. And because it's the successor, that means that this is like the right position to put it in, as it's the next element greater than A, but it's also less than B. So it's on this side, so it's less than B, but it's also greater than A. If you put it here, that would mean that it's less than A. Or, yeah, so it wouldn't have been on this side at all. It would have been left of A originally. But just so you guys get a bit more knowledgeable on the rotations, because that's the type of questions they'll ask you. A tracing question is usually something that they want to give. Let me move over back and go over the other rotations real quick. Yeah, so right rotation, same thing as left rotation, except now you look at the left node and you rotate it up rightward. So you could see around the same logic as left, but you see now it ends up balanced. So we take the left node and rotate it rightward. Any questions there? Okay. Okay, now for left-right rotation and right-left rotation. So essentially what happens here is that if we were looking at C, we see it's unbalanced, right? But because if we just did a right rotation here, I'll show you what would happen. And hopefully I could do that pretty quickly. Yeah. So if we just did a right rotation on C, what would happen? We'd have A go up, and then C would become the child of A, and now B would become the child of C because of that rule, remember, with the successors and predecessors.
So B would be a left child of A. I think.
Did I mess up?
Yeah, B would be BAC, because that's valid.
No, hold on.
Okay.
No, this is right. Yeah. So now A would move upward, C would become the child of A, and now with C's left side being available, since it was connected here before, it is now has the availability to take on B as the child. So it's still unbalanced. That's the problem we have here. So to generalize it, I think I wrote it down here. We have to do a left-right rotation because it's kind of confusing to know when to do a left-right rotation, especially if you're looking at it from this node. You perform a left-right rotation if you have to perform a right rotation, but the node to the left has a heavier right side than the left side. So what that means is, I think if the height of the right side is more than the left side. So it's a bit of a mouthful, a bit of a lot to remember, but generally, you're not going to have to code that. You're just going to be able to visualize it. So you don't have to like imagine the height. You could just see that, oh, the right side is clearly larger than the left side. Because like imagine if we had a node here that was D, then we could just perform a right rotation. However, if we had another node E, then we have to do a left right rotation again, because this side is heavier. You could try it out and see yourself how it works if you'd like, but it's going to take a little bit too long to do that example. But proof by trust me? Okay. Let me move on to right-left rotation. Same logic. So right-left rotation is the same as the left-right. Right-left rotation is the same as the left-right rotation. I feel like I'm saying the same thing, but I'm not. It's very weird. So it's the same, except it's the other direction. So now we have to do a left rotation, but we can't because the right child's left child is heavier than its right child. I don't want to continue saying this. You guys get the point, right? Any questions about left, right, left rotations or rotations in general?
Alright, so I'm gonna take it from here because I modified my slides.
Is there two? Oh, you did? Okay.
Yeah.
I'm going to pass it back to Dylan, and he's going to do the rest of the slides.
Alright, I did some changes to the AVL section because last night we decided to hand it to me. So I'm gonna take over now. I just needed a break, needed a drink. So when it comes to inserting and deleting in AVL, it is basically identical to a binary tree at the start, right? We're gonna perform a binary search tree insertion or deletion at the beginning, and then we're gonna assess whether or not we actually need to do any sort of rotations to keep it balanced, right? At the end of the day, we still do have that search property in an AVL. All left must be less than, all right must be greater than, so on and so forth. So insertion and deletion, exactly the same. But as soon as you're done doing the binary search tree insertion or deletion, you're going to want to go ahead and calculate the new balance factors, and then you're going to want to do rotations if necessary, right? And so I want to talk about the ABC method. This is the way that I personally remember it. I know Leo didn't bring it up. I really like this way because it stops me from having to think about right, left, right, right, left, right, left. I just kind of look at it and I'm like, all right, let's do this. So let me switch to my tablet. So as we can see here, in this example, I didn't want to do the rest because I wanted room, but we just inserted 2, right? So 2's been inserted. When you calculate the balance factors, you want to go bottom up, right? Reason being is when you insert into like this side of the subtree, I'm not drawing properly, and like this side of the subtree, we want to perform all of the rotations on that side because we're trying to like isolate it, if that makes sense. We want to minimize the number of rotations we have to do because that's computationally expensive. So we've just inserted 2. This has a balance factor of 0. This is 1 minus 0, which is just 1. This is 2 minus 1 because right, left minus right. Left is a height of 2, right's a height of 1. It's going to be 1. But then 8 right here, we're going to have 1, 2, 3 minus 1, which is going to be 2. So we don't want this, right? This is not a good balance factor. And so what I like to do is you're going to circle the node that has the bad balance factor. And then, the hell? Just turned on me. Anyways, you're going to go in the direction where it's heaviest, and you're going to circle 2 more nodes. So in this case, obviously the left half is heavier than the 11, so we're going to circle 5. What's our third node here going to be? What do you think? 4. All right. So we have our 3 nodes. And now we're going to need to determine our A, our B, and our C. How do we know the way we want this? It's a binary search tree. So A should be the node with the smallest number, C should be the largest, and B should be the middle. So in this case, C is A is 4, and B is 5. We're going to ignore everything it's attached to right now. We're just kind of looking at this subtree right here. All right, so don't bother everything up top. So we're going to, we want our end product to end with, right? Because that's the property that we need to maintain. So I'm going to make like a little copy of this tree over here. Just the subtree, not the whole thing. So 8 And we're only going to, we're not going to concern ourselves with this children. We're actually going to, we're going to do them as straight lines. So we'll do 8, 5. Shit, I'm running out of room, man. Okay, hold on. 1 second. 8, 5, 4. And so we want to assign its children, we can call them as t's, right? So ignoring what they actually are, this is t0, t1, and we're doing this from left to right. This is t2, this is t3. Do we see how I did that? I went from left to right, right? And so now, what we're going to have is we want to end with A, B, C. So 4, 5, 8. And now in the same manner that we went left to right, we just assign left to right. So this is going to be t of 0. So let's go back over here. T0 is 4's left child, which is 2. So this is actually 2. Then we're going to assign t of 1. T of 1 is 4's right child, which is null. So we're actually going to leave this empty, right? Because why would I write a null node? And then, actually, I'm just going to write an x just so we can kind of understand what I'm doing here. And then we're done with this. T2 is 5's right child, which is 7. And that goes here because we're going left to right. And then T3 is 8's right node, which is 11. So I'm going to go ahead and erase this because it's a null node. And then after you're done performing that on the subtree, if we look here, this is a balanced subtree, right? High to the left, high to right, all good. We're going to go ahead and reattach it to the rest of the tree. So this goes to 12. This goes to 18. And then this goes to 17 as is. This has a depth of 3. The right has a depth of 2. Height factor of 1. See how I did that? A, B, C, T1 through, I think the maximum would be T5. And then we just reassign, we rotate how we want it, reassign, everything's good. Notice how I didn't say the word left or right. Well, actually, that's a big lie. I didn't say left, right, or right, left. But I did say left and right. So I like to do it that way, just to kind of abstract that logic out of my head, because it's confusing to me. Do you guys like that better or worse than having to identify right? Yeah? Feeling better? Okay, good. I hope so, because that's the only way I know how to do it. So the type of problems you're going to get, they're going to be tracing. You're either going to trace an insert or a delete. And that's exactly what our two problems for AVL are. We're going to have an insert and we're going to have a delete. All right? So for our insert, we're going to show the final result of inserting 48 into the AVL tree below. Could someone tell me where that's going to go? Without any rotations, where will it end up?
Right to the right of 45.
Right of 45. All right, we're good. We're correct so far. So again, we're going to calculate the balance factors moving up from bottom to top. So this guy has a balance factor of -1 because it's 0 minus 1, that's -1. The 37 here has 1 minus 2, -1. We're looking good so far. 25 up here, that's where things get a little actually, no, we're good. It's 2, and then 2 minus 3, -1. And so our problem child right here is going to be 50 because the left side is 1, 2, 3, 4, and the right side is 2, which gives us a value of 2. So we've determined where our problem child is, right? So we're going to do the ABC method. This is our first node. What are our next two nodes going to be? 25 and 37. We're going into the heavy side where we found our problem. And so we're going to assign our A, our B, and our C. So in this case, our A is what? 25. Our B is 37, and C is 50. Awesome. So let's go ahead and redraw them with the T notation. So right now we have 50, 25, 37. So what right here from left to right, this is going to be T1, T2, T3, T4. Again, we saw how I did that, right? All right. So now, ideally, we want A, B, and C to end up like 37, 25, and 50. We all agree on that to maintain our search property. And so now, from left to right, we're going to assign all of our different T's. What's up?
Can you explain why Can you explain again how you got 37 to be the new root?
Because we always want B to be in the middle. So don't even think about it as a root. Right now we're just looking at these 3 nodes. In our head right now, none of this exists. We're just looking at those 3 nodes, right?
And you looked at that because that was the heaviest side.
Because 50 is the one that triggered the balance, so that's one of the nodes. And then you're gonna pick 2 more nodes going into the direction of the heavy. So the left side is more heavy, we pick 25. And then between the left and the right, this has more nodes, we're gonna pick that one.
Okay.
And that's also where we also want to go in the direction of the mess up we made. So in this case, we inserted 48 on its right as well.
So you want to go into the heaviest first.
Exactly.
And
And look here, this is a height of 1, 2, 3, and this is a height of 1, 2. So that's why we went right to 37 instead of left to 12. Gotcha? All right, awesome. So we have our 3 nodes, A, B, and C. And now we want to assign all of our T's from left to right. So what should go here? T1, right? What is T1 in this case? What's T1? It's going to be 25's left entire subtree. So that's going to be 12, which is attached to what? An 18. We take the whole tree. So when I say T1 this way, I mean the entire left subtree, not just the left node. Notice how I pulled the entire thing from the left of 25. Right? So that's T1. Next is T2, which is, as we can see here, 37's left subchild, which is just 36. So 36 goes here. Next is T3, which is 37's right, which is this. So 45. And then 48. And then the last thing is T4, which is 50's right. That's going to be 80 and 90. And so, let's do the math here. This has a height of 3. The right side has a height of 3. The left side has a height of 3. Our root is 0. We're looking fine and dandy. But now let's check. Is this a binary search tree? Everything to the left of 37 is less than. We have 25, 12, 36, 18. Everything on the right is greater. Same can be said about 25 and 50. Everything looks good. So how do you guys like that ABC T1 to 5 method? When I saw that, like, my mind opened up. Like, I had an enigma. It was crazy. It was an epiphany. It was great. Awesome. Cool. So, as you can see right here, our final thing is here. So, 1 point with AVL right values. So they actually do want you to do the values for these guys right here. Good here. So 1 point for 37 at root. Jeez. We have 37 at root. Oh my goodness. Right? I can go back and forth to make this easier. So look, we got 37, 25, 50. 37, 25, 50. 12, 36, 45, 80. As you can see here, we got the same tree. Right? Feeling good about that? All right. So now let's do the next problem, which is going to be right here. I'm going to move it over one. Everything's good. So now we're going to perform a deletion, right? And just like a binary tree, the deletion is pretty much going to be the same. So we're deleting the value 8 from the AVL tree. This is fine. The result of deleting 8 from the process, there are 2. So they tell us exactly how many rebalance operations there are. And that's why I say go from bottom up. Because when you rebalance the left tree, it might not be enough and you may need to rebalance like the whole damn tree. So go from bottom up, right? So we're going to get rid of 8. And so now, why is that an issue? The issue is 15 now has a balance factor of 0 minus 2, which is greater than an absolute value of 1. So we're not in a good spot here. We need to do some rebalancing. So we're going to start with 15. Why? Because 15 is the one that triggered the rebalancing from bottom up. That's the one. So what is our A, B, and C going to be here?
15, 23, and 18.
15, 23, and 18. This is a pretty straightforward one because there's really no children to move around. All we need to do is just do this, right? We need to do, so after our first rebalance, it's literally just going to be 15, 23, no, I'm lying, 15, 18, 23. And so see, this is an example of what I was talking about. This right here is classified as a right-left rotation. Notice how I didn't have to think about that. I just circled 3 nodes, A, B, and C, assigned them this way down here, right? So that's the ABC method. So we fix this, And now we can attach it to the rest of this other tree. So 27, 49, 46, 60, and then 35, 53, 70, and one more node, 58. All right. So now this is the tree that we're working with here. This is what we've made after the fact. And so I'm going to clean it up a little because we actually have to like look and work with this. So I believe, say 49. Pardon my terrible handwriting yet again. And this goes down, it's actually this one that's 53. All right, so the issue is now this left subtree has a height of 2, and the right one has a height of 1, 2, 3, 4, right? So now, who has the issue? It's the root. So the root is going to be what triggers our rebalance. So this is going to be the balance factor. So 27 is now one of our nodes. What is our other two going to be? Forget A, B, and C right now. Just which three? 49 and 60. We're going in the direction of the heaviest weight. And so again, we already know how that's going to end up. We're going to end up with 49, 60, 27. And so now we need to start assigning all of our T's, right? So to the left of 27 is going to be T0, T1, T2, T3. An important note of the T rule. Notice how I didn't take the right subtree of 49 as one of my T's. Why is that? Because its right subtree is one of the nodes that we're rotating on. So we ignore those. So we have our T1 through 3. So let's or T0 through 3. So let's assign them. What is going to be to the left of 27? It's going to be actually the same subtree as before. So it's going to be 18 to 23 to 15. Now, the next one is going to be T1, which is this subtree right here. So it's going to be 46, 35. I think that's it for that one. My handwriting's poor, but yeah, that's it for that one. And so the next one is going to be T2. And where's that going to go? Left of 60. Perfect. The next open spot, 53, 58. And then T3, 70. And so those are our two rotations. I'm really sorry for the poor handwriting. Can you all follow what I'm talking about here? Good? So let's see if I can go back and forth super fast to show you that we're right. So for the first one, top row is 27, then 18, 49, we're good. Then 15, 23, 46, and 60, we're good. 35, 53, 70, we're good. 58 at the bottom. Now for our second iteration, looking at the right half, 49 is the root. Next row is 27 and 60. Then 1846, 5370, 1846, 5370, and then at the very bottom, 1523, 3558. So we did it successfully. We did two successive rotations. Everything worked good. Any questions about AVLs as a whole, before we move on to our last section tonight? Any questions? Y'all like that ABC method? I'm a fan. I like it. All right, cool. Glad you guys agree. So, last but not least is sorting. Sorting, you need to remember a lot, unfortunately, because you need to know 5 different sorting algorithms. You're expected to know the 3n squared ones, which are bubble, selection, and insertion, and you're expected to know the 2 log n ones, which are quick and merge sort, as well as the differences between the two. So I'm going to go over that. So like I said, there's 2 different types. There's n squared and n log n. You need to know the difference between them. So before I even go into this, just so you can kind of understand what's going on, a lot of your problems are either going to be tracing a sorting algorithm. They'll give you a table of an array and say perform selection sort and draw the array with each iteration, which is going to be our example for today, right? Or they may have you do a small segment of code. Sometimes they may have a fill in the blank bubble sort where like pieces of the code are missing and you fill it in. Or you may have to write a piece of the merge or the partition function, which is usually the less popular ones. But they do have most of it, and it's fill in the blank. It's not like fully write a merge sort from scratch. Hell no, absolutely not, right? It's majority of it's done. You just have to do the piece that's missing. So for bubble sort, the algorithm is pretty straightforward. But you need to remember, here's the biggest note that I have. A swap happens at each check, right? This is why bubble sort is so damn slow. Because every time it checks, whether it's gray or whatever, it always makes a swap. So this is the slowest, even though all of them have a big O of n squared. This is the slowest of the n squared algorithms, right? If you did a speed test between the three of them, bubble sort is significantly slower than selection and insertion. Anyways, essentially what bubble sort is you start at the first number. And then you go, is the right one bigger than me? If it is, swap them. And keep doing that all the way till the end. Now keep in mind, when it's not greater than anymore, we don't stop that iteration. We just proceed to the next number. So for example here, it looks like this is a less than bubble sort. It's going backwards. So I won't actually show this. I'll show another one. But yeah, that's bubble sort. Everyone got bubble sort. And the way you can think about it is each swap is like, imagine you have, the reason they call it bubble sort is like a bubble in water just slowly trickles and matriculates up to the top where it belongs. All of the elements sort of bubble up to the top. So that's why it's called bubble sort. Selection sort, pretty nice. You're going to iterate over the entire array, and you're going to select the greatest element and move it to the front, right? So in this case, don't worry about any of this. What we're doing is we're looking at this, and we're looking for the greatest value out of here, which is 20. We then swap 20 and whatever's at the end. So that swap was made. Keep in mind that a swap does have to occur. It's not just an outright override. So that's, again, something you have to do in your tracing problems that they always get you, trick question. So you start at the first, and there's two ways you can do it. You can start at the first, look for the smallest, insert at the front. Or you start at the first, find the biggest, insert at the end. Either way, you're doing the same thing, right? We understand the difference? We're selecting the smallest to put at the front, or we're selecting the biggest to put at the end. And we keep doing that. Insertion sort's the more complicated one. People tend to not really understand how insertion sort works compared to the three of the n squared sorting algorithms. So essentially what the insertion sort does is we're creating a sorted partition of our array. And don't be confused with quicksort partition. Let me see if I can show you what I mean. So this right here is our array, and we're actually going to consider the first, that's not good. I'm gonna speed through this. So we're gonna consider, wait, Leo, do you have your battery pack? Yeah, could you get me that? Because my charger's bad. Anyways, in this case, we're considering this to be the first sorted segment of our array. So you see how it's green? I don't know if you can tell up there. The color is really faint. You see the green? So this is now a sorted part of our array. And then what we're going to do is we're going to make this our sorted part. But it's not currently sorted. So what we're going to do is we're going to keep swapping to the left until that's the case. So see how 1 goes over here, becomes 1, 23, and now this is sorted. Now, the way it works isn't really evident. USB-C, Ricky. You ain't got? No, you good.
USB-A to C?
Yeah, USB-C. It gets more evident when you get to longer sorted partitions, right? So now in here we absolve the 10, we eat it into our sorted segment, and we just keep putting it to the left until our sorted segment is actually sorted. Do we kind of see how that's working? I know that one's a little more complicated compared to the other n squared sorts. But with that complication comes a save and runtime. Out of the three, this one is the quickest, even though they're all big O of n squared. So again, at this point, this part is sorted. We grab here, 2 keeps getting inserted down and swapped until it hits the end, and then we have our inserted part. My iPad hates me right now. It's like charging and draining at the exact same speed. Okay, I had a sort visualizer up here. Do y'all want to do that or not? It's late. Do y'all want to do it? Show of hands who wants to see it, and I'll explain it as we go. All right, I'm feeling a little less than half, but screw it. We don't need democracy. I'll do this anyway. So let me go to the n squared. There are so many sorts on this site, but I'm going to go through just these for now. And we're going to get that nice, like, brain sound. Wait, it's not playing out of the audio. Wait. I want to hear it, guys. Hold on. Okay, I think we should hear it now. I lied. Anyways, so this is bubble sort. I'm going to bring it down to a very small number of elements so I can kind of demonstrate what's going on here, right? So as we go up, wait, my bad. So what you're going to notice here is the biggest element is going to keep going up to the front. So it bumps into the biggest and grabs it, and it keeps going. But notice how, see this one? Like, I wish I could slow this down. Notice how this one, here. This is the emphasis I'm trying to make, because this is the trick question where people get. So why does it undo it when I press play? Okay. What I want you to notice is that if we have a small one, it's going to keep bubbling up, like a medium-sized one. It's going to keep bubbling until it hits a big one, and it's going to stop. And then that big one's going to continue to go up. What I'm saying by that is that multiple things could have a swap in an iteration, and you'll see that in like some of the tracing problems. So this is bubble sort. You see the biggest one keeps going up to the front, and each step there's a swap happening, right? And you can tell how slow this one is, because look, we're waiting here for a while. Okay, cool. The next sort is selection. So notice here, with every iteration, there is no like massive swaps going on. It's just going to swap the biggest element from its position to the end. So watch, we're gonna see this guy go to the end, and then next we're gonna see this one at the end, and this one right here. So follow with me. Okay, this is the smallest selection sort. Now I look stupid. It's grabbing the smallest one and moving it to the start every time. But a similar philosophy, right? We're selecting one and moving it to the end. So this is good where it's at. Then this will be swapped with this one, and then this with this one, so on and so forth. And as you can see, the smallest keeps building up from the start. That's selection sort. Now insertion sort is a little hard to see with small number of elements. So I'll make this one more like 50. You're gonna see how all of this little piece over here keeps sorting itself, and that sorted thing keeps growing. So look, to the left, you see how the left looks partially sorted now? And as we add one element at a time, it gets inserted down into that sorted segment. So you see the left hand now looks almost sorted. And each time we grab a new one, it keeps going in that sorted segment to its correct spot. You guys see that relationship I'm talking about? We grab that new element and insert it into our sorted segment. What's up?
In those examples, or like those sorting algorithms that you can do either from like smallest to largest or largest to smallest, are we supposed to do it in one specific way for that?
If they want it in a specific way, they'll tell you. Or if they don't tell you, so for some of them, they'll be like, okay, I want you to perform an insertion sort, but we did the first iteration for you. That will be enough for you to know, okay, are we inserting, or are we making it biggest or smallest first? So that'll be enough to tell you. So does everyone get good insights out of that little sort visualizer? Feeling good? Awesome. So let me go back to the slides. All right, so we went over our visualizer. Now we're going to the n log n sorts. So the n log n sorts are what's called divide and conquer algorithms. We're basically splitting up all of our work into a bunch of little tiny tasks, and those tiny tasks are a lot more optimized and performant than the big picture, right? So for a merge sort, we keep splitting the array until our array is of size 3 or less, right? So this is the splitting step up here. And then when we hit our base case, on our way back up, we're going to call the merge function on the array at those specific points. So what the merge function does is it takes those two arrays, and the biggest distinction is it copies them into memory because we need to hold on to them. So that's a big thing about merge sort that I'll get into. It's just going to grab the two of them, and it's going to look at the front of them, and it goes, okay, this one, the front is less than, so I'm going to put it in. And then this one's left than, and it kind of just merges them. So here's an example. If it were on these two arrays, here, let me go ahead and demonstrate on the iPad yet again, because I think it helps. So imagine we're on the merge call with these two arrays, right? And we're looking at these two arrays. What it's going to do is we're going to keep a pointer here and a pointer here. And it's going to go, okay, 3 is less than. I'm going to put it here, move my pointer forward. And we're going to check again. Which is less, 27 or 9? 9. So we're going to put 9 in here, and we're going to iterate the pointer forward. And we continue doing that until the entire array is made. So we do 10. 27 is less than 82, so we do 27. 38 is less than 82, we do 38. 43 is less than 32, so we do 43. And then we do 82. Do you see how that merge function works? We're essentially looking at the front of both of those arrays and just putting them in as one is less than the other, right? But something else that's important here, actually this example didn't show it. I'll have to go into that when we get to the code. So that's merge sort. Quick sort is a little bit different. What quick sort is going to do is it's another divide and conquer algorithm where we're sort of sorting the left and right halves on our way back up. But it's a different strategy. It's called partitioning. Essentially what a partition is we're going to find some sort of element, and we're going to make it so that every element to the left is less than, and every element to the right is greater than. Will each of those elements be sorted on the left and right halves? No. So for an example, right here, this is true, because everything to the left of 5 is less than, and everything to the right is greater. But notice that it goes 4, 3, 1, 2. Like this right here is not sorted. That's an important distinction between pivot, or with the pivot with quicksort. So then we go here, and so in this case, the pivot is 2. And notice, I believe they always pick the end. So there's a bunch of different partitioning strategies I can go into. So for example, in this example, we're picking the last element as our pivot every time. Because notice how 6 becomes the pivot here, 2 becomes the pivot here, right? And there's a bunch of different ones. You could do random, you could do end, you could do start, and we'll go into some of those issues in a few. But essentially, we make sure that all of the pivots are in the correct position at their respective subarray. And then eventually, when we get to an array of size 1, the pivot's in the middle, and it's sorted, and all of the pivots above it are sorted. So do you see how this kind of... Imagine this is one array at the end. Like this comes down to 1, then 2, then 3, then 4, then 5, then 6, right? Cool. So here's the interesting thing about quicksort. What happens if the partition we pick every single time is the smallest or the biggest element? We're essentially doing a glorified bubble sort because we're going to have to swap it all the way. So imagine it's at the end and it's the less that, or the least. We have to swap it all the way to the start each and every time. So the interesting thing about quicksort is that its worst case is actually n squared. So then why do we call it an n log n sort? It's because on average, in a completely randomly uniform distributed array of numbers, there is an equal likelihood for every single number, every partition strategy to end you with n log n. But it is the average case. So why do we even bother implementing quicksort if merge sort has a better worst case runtime?
Because merge sort's memory is O of n.
Merge sort requires more memory. So I'll go back here. When we merge these two arrays together, we have to create copies of them in order to work with both of them at the same time. And so all of this memory right here exists until we end with our final result. So imagine a array with like a bajillion elements. Imagine we have an array that is just so many different subarrays being merged, right? Like array, blah, 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 blah. Let's just like say this goes on forever, like huge numbers. The depth of this part of the tree, imagine how deep that can end up getting. And all of that memory is staying there until the final array is resolved. So that is the biggest issue with merge sort and why quicksort is a contender, despite the fact that merge sort has a best, worst, and average of n log n. So that's an important caveat you need to understand as a computer scientist, and they do ask that on the exam. Explain the difference between quick and merge. Explain how merge can be worst case n squared. You need to have a good understanding of these two sorts conceptually under the hood, right? Not just tracing and coding and all of that. Because that's where a lot of people lose points on sorting, is all of the conceptual questions between merge and quick. Any other questions, the difference between merge and quick? Any conceptual stuff? No? All right. So here, I went over exactly that. Quick sort, worst case, n squared, but the average is n log n. The memory complexity is O of 1, but you don't need to make any memory extra because it's all done in place. That whole pivot strategy is done on the same array, no extra arrays needed. N log n is merge sort, right? Worst, average, best, all n log n. But the memory complexity is O of n. What's up?
Do you have to know anything about stability for the condition set?
Stability? For quicksort, you could say that it's unstable because n squared, because there's a chance you have that. So that's why it's unstable. So if you know that, you know that as well, right? How it could be n squared. So, like I said, the way that it's an n squared worst case, if we pick the worst partition every single time, we will need to swap that element with every other element n times. So it's n squared, right? And that's how you need to know the case where the partition is the worst, right? So the two types of problems you can get with sorting is tracing or coding, concept coding and stuff like that. So I'll go ahead, and we can go ahead and get started with some of these problems. Let me open it up on the iPad. All right, so this one's a little complicated. So essentially what this problem is they want you to code up the remaining part of the merge sort. So complete the following merge function that is used as a part of the merge process. The function performs the merge operation from left to mid and mid plus 1 to right in the index of the array. So all of this is basically saying, hey, we're calling this function from the actual merge sort function. You don't need to worry about that. So again, this is the merge part. The thing that we're concerned with here is we're concerned with this process right here in the middle, right? We're trying to merge those two arrays together. And so let's see what they've done for us so far. This right here, they're giving us the size of the left array, the size of the right array. They're making our life easy here and saving us an easy mistake by changing the bounds. So we got some good stuff there. They're actually creating the arrays for us, and they're copying all the data into the arrays, right? So as of right now, we have given to us essentially are these two arrays right here. So the only thing that they want from us is they want our strategy to merge the two of them together, right? And so the way that you're going to do that, we have I and j, which is our index. I is going to be our index in our left array, and j is going to be our index in our right array. And k is going to be our actual like position in that array, in like the big parent array, right? So let's go ahead. I'm going to write the code to the right. You could imagine that it's underneath it because, you know, functions are top to bottom. But essentially what we're going to do is while we have both of the arrays still there, so like we have to keep going. So while I is less than n1, so this is saying we're in bounds of the left array, and, or no, it actually should be or, because we're going to empty out the arrays as we go. So imagine that the first array is shorter than this array, and somehow this array completely depletes. We want to keep, and let's say we use these two. We want to keep going and removing the remaining on that array. So we're going to do while or, right? J is less than n2. So this is while we're in bounds. And all we're going to do is we're going to say if j equals n2 or, I'm going to run out of room here. Let me lasso over here. So what this j equals n2 thing is saying, if we've ran out of the right array, right? So we have two conditions where we want to use the left array. Either we're out of the elements on the right and we've hit our bound, or the elements, this is for when we're using the left array, sorry, or if L of I is less than right of j. Right? Oh, we also have to check if I is also less than n squared, or not n squared, sorry. I is less than n1. Hold on. And I less than n1. All right. So this is saying we're going to use the left array. we're going to say array at k equals L of I plus plus, else, and we're going to have to also check, actually we don't need to check. We're just going to do else. So this is saying that we're basically done here. This means we need to do the right half of the array. We're going to say array of k equals right at j and j plus plus. And then the last thing in the loop, we need to increment k forward 1. Everyone understand how that works? Now there's another way that you could be taught to do this. The way I personally like to do it, but takes a lot more room, is I do and, so while both of them exist, and then underneath them I just have 2 while loops emptying out the other 2 arrays if they exist. That's how I personally do it. But again, limited space here, and when you're on that exam, you're also limited on space. I believe they'll give you scratch paper if you ask, but then you have to like be like, hey, look at scratch paper number 3, and you have to like do all that weird stuff. So try to keep it concise if you can. Any questions about this code right here? Everyone good? Question? The top? So this is so that we can combine it into one. So we're basically saying if we did and, imagine that. So imagine these are the 2 arrays, right? And we're at a point right now where this left array is empty, but this right one only took 1. This condition would become false, and if it were and, the whole loop would break, even though there's 3 more elements to be dumped out of that array. So that's why it's or. And the reason we keep it at or is so it can continue to do that, and that's why we do a bounds check here, basically saying like if there is, so the reason we'd use the left array is if j is equal to n2. That means the right array has been completely depleted, or it's just less than. So that's how we're handling getting rid of an empty array. Does that make sense? Yeah? All right. So we have here, same type of principle. So we're saying while either exists, if the right is full or the left is less and in bounds, we do left increment I. If that's not true, then we use the right, and then we always increase k at the end of the iteration. Everyone good on that? Last problem, then we can all get out of here. Selection sort, I believe. Yeah, so show the result after each iteration of performing a selection sort. And so here's the thing. There have been some, your question, we can go ahead and get rid of this, even though you probably read already that they said the maximum, even if they didn't tell you. If we look here, from iteration in 0 and 1, what do we notice have changed? 16 and 5 have swapped, which means we've been inserting our maximum. We've been selecting our maximum. So now we know it's a maximum, right? So can someone remind me how this selection sort works, generally speaking? We find the biggest element and insert it into the next, the furthest unsorted position. So what I like to do for selection sort, I actually like to check when something's sorted. I do this for all of my sorts. Like this is good, this is in the right place, it's never gonna move. So 16 is good, right? And so I'll drop 16 down since it's already checked off. And so now we're gonna look here, what's the next greatest element? 15. And so now where 15 used to be, we need to put it with its new position, which is 10. 15 is now sorted, and we drop the rest down. Now the next greatest from here is what? 13. So 13 goes here, and in place of where 13 was, what goes on the 0th index? What goes here? 10. We drop the rest down, so on and so forth. 12 is already in the correct spot, so we literally, that counts as an iteration though. That's the trick question in this. So we did the whole iteration to look for a greater one, and it didn't exist. So this is an iteration, all right? That counts as your 4th iteration. So that's probably where a trick question is on this problem, because 12 is just already in its sorted position. So again, we're gonna drop these down. Our next greatest element is 11. 11 is gonna be swapped with 5. We're gonna have 9, 10. They're all in the correct spot. And then We have 10. I lied. That doesn't count as an iteration. Or no, yeah, they do the last one for us. So the next greatest is 10. That could swap with 9, 5, 11, 12, 13, 15, 16. And then the last iteration, the 7th iteration, they do it for us. 5 and 9 are swapped. And this is our sorted array. All right? So let's juggle back between the solution and the problem here. So 13, 11, 9, 5, 12, 10, 15, 16. Boom. The biggest thing I want to point out here is, did we have that non-iteration happen? So where's the iteration that was a trick question? It was right here. These 3 and 4, the rows are the exact same. 3 and 4, the rows are the exact same. So you guys see that, right? You see how they could have tricked you there a little? You could have had an empty row. 1 point for each row. Row has to be completely correct to get the point. So that means if you mess up early, you're honestly kind of screwed because it's going to mess up your whole selection sort thereafter. With that being said, any questions on sorting? Awesome. Thank you for being patient with us. I'm sorry today was a bit clunky. Tomorrow, same time, same place, we're going to be going over bitwise.